This is a good news, bad news situation. The bad news is our Chapter 8 discussion is going to be a long. There are lots of slides to cover. Good news is this is the last chapter for the course. So this will be, we'll get done with it today. After we share. Go, now let's make a slideshow out of it. Well, let's see. There we go. All right. Now we're sharing, and let's see, are we recording? Stop share, screen share. Supposed to be. I'm going to have to make sure. Yes, recording. All right, let's share again. All right, I hear thunder outside, so this video might get interrupted and I have to restart it. Okay, Chapter 18, the universe. We worked our way up from classical physics through quantum physics, through the Earth, solar system, small solar system bodies, and now we're looking at the universe. All right, what do we mean by the universe? It's sort of intuitive, but in sciences it always helps to have a definition to go by. We're actually talking about the totality of all matter and energy and any space in which they reside or operate. And that includes stuff that we can't even detect yet. So universe is everything. So in this chapter, we're going to look at stars. We'll reference the sun from time to time, but we're looking at all the other stars too in the universe and how they organize themselves, particularly into galaxies. And then we'll look at cosmology. Cosmology being the study of the structure of the universe and how it got that way. All right. So how do we gain information about the universe? Primarily through light. Except for a handful of spacecraft that have been sent into our solar system, and a couple of them who are outside the solar system now, everything we know about the universe comes primarily in the form of light, electromagnetic radiation. Stars, galaxies, they emit parts of the full spectrum of light. For many years, astronomy focused on, not a pun intended, focused on electromagnetic radiation of a particular part of the spectrum, and that was the visible light. So all of our optical devices were designed to receive visible light. And for the longest time, that's all we knew existed. But gradually, science detected and proved that there were other forms of light. So in 1931, the first radio telescope that detected the wavelengths in the radio part of the spectrum became operational. It actually started out as a project to detect wavelengths that could interfere with communications. So Carl Jansky, of the Bell Telephone Labs, set up this radio telescope, and it would only detect signals of one wavelength, 20.5 megahertz. And his research was to investigate possible sources of interference with radio transmissions for the company. So we'll come back to radio wavelengths in a minute. The other fly in the ointment is that the Earth's atmosphere absorbs selectively in the electromagnetic spectrum. There's some, and this chart, I think you've seen this one before, but it's good to review, is set up so that the higher the line here, the more absorption, atmospheric opacity. So if it's 100%, that means nothing's getting through. Gamma rays, X-rays, ultraviolet. Now, ultraviolet is sort of right on the cusp of some of it gets through and some of it doesn't. That's why ultraviolet radiation for safety purposes is divided into a couple of bandwidths, the A's and the B's. And one of them, I forget which, makes it through the atmosphere in sufficient quantity to burn your skin. And there's potential for skin cancer. But another of the bandwidth doesn't make it through. So you'll notice here with this drop-off, on the purple side of the visible spectrum, now you're starting to get some UV penetration. Not a lot, but enough. If you spend some time in the sun, then you may get enough to cause problems. Most of the visible part of the spectrum makes it through the atmosphere with some absorption. There are other things that interfere with observations through the Earth's atmosphere, and we'll talk about those in a few minutes. Now we get into the infrared, and there's a good bit of penetration through some of the infrared radiation makes it through. Some of it doesn't. But the radio waves, they, in this band right here, between about, say 6, but well, actually closer to 4 or 5 centimeter wavelength, up to maybe 12 or 15 meters. That range right in there is where you can operate your radio telescopes. Let's see, what was it Jansky operated at? 20.5 megahertz. All right, this is wavelength. So if we want to know 20.5 megahertz, let's see where, there it is. That's times 10 to the 6th hertz, right? And then we have the speed of light is equal to wavelength times frequency. So this is 2.9979 times 10 to the 8th meters per second is equal to this times that. So we solve for this, divide this one by that one. So if we divide speed of light by the frequency, wait a minute, that's my mistake. That's the frequency, right? This is wavelength. Okay, so if we divide 2.9979 to the 8th power, divide that by Hertz, 20.56. Okay, so that's 14.6 meters. So that's the wavelength at which Jansky was operating. So he was way up on this end, it's right about on the edge, because this is a logarithmic scale. See that 1 meter to 10 meters, and then 10 to 100, right? It's not linear. So he was operating at this range, and it's since been discovered that there's a whole range down here at which radio telescopes will operate, so to speak, with impunity. Longer wavelengths have trouble getting through the, actually not the atmosphere. The longer wavelengths have trouble getting through the ionosphere. So we have an ionized layer of atmosphere at the very top. It's there because of solar radiation is ionizing the gases in our atmosphere, plus the magnetic field of the Earth is concentrating them in that layer. So these wavelengths can't get through. They're absorbed up there, but these do. Okay. So scientists, when you can't observe from the Earth's surface, then you need to figure out, how do I get around that? Minimize the effect of the Earth's atmosphere. Well, there are a couple of ways you can do it. Right? One is you can locate your telescope on top of a mountain where the atmosphere is really thin. And most high-end telescopes are located on top of mountains and in very dry, stable atmospheres, high altitude. You can send, some telescopes have been sent up in balloons, right? So they observe for a limited amount of time and then they come back down. Some have been placed in aircraft that fly at very high altitudes. Some are put in satellites and spacecraft. Right? The Hubble Space Telescope has been up there for quite some time. I should know the date when it went up, but I can't remember. I think it was in the 1990s. And it's had several spacewalk missions to upgrade and repair. Now we have space-bound telescopes that are not in Earth orbit, but some of them are in sun orbits, or they're in extreme orbits above the Earth or further out. In fact, the James Webb Space Telescope is designed to reside at the L2 Lagrange point, which is about 1 million miles on the other side of the moon. Okay, so those are the ways that you can solve this atmospheric problem of observing through telescopes. This is the list of the telescopes that have been launched and are still operational. So we have those that operate in the gamma range. There are only 5 of those left out of 16. X-ray, 9 out of 36. Now, why do these instruments have limited lifespan? Why can't they just go on forever? Well, there's several reasons, possibilities. One is power. Okay, if you have solar panels that are functioning, then you can get power to operate your instruments from the sun. But solar panels have a limited lifespan. They become less and less and less efficient over time. Eventually, they can't produce enough power. Or you could put a nuclear generator in there. A thermonuclear generator, that's not a bomb. It's a It's a type of electrical generator that we put on spacecraft that are going deep space. New Horizons, both the Voyager craft have nuclear electrical generators, so they can function indefinitely on that. But you also, depending on where your orbit is placed, where your spacecraft is placed, you also may need fuel to make course corrections, to reorient your telescope for different parts of the sky. If it's in Earth orbit, then you may have to add a little delta V, change in velocity, in order to keep it in orbit, because the Earth's atmosphere, as tenuous as it is, goes out for hundreds of miles. And there's a slight drag on all spacecraft in Earth orbit. So occasionally you have to give them a boost. Otherwise, they just fall back to the Earth and burn up. Okay, let's get back to our list. We have 8 operational telescopes in visible range. We only have 1 IR telescope at present. 11 have been launched. Now, another point to make is that this many were launched, but sometimes the mission fails and they don't even become operational. And I don't have the data on that, which ones of these did that. Some of them blow up on the launch pad. And that's why they have insurance. Radio telescopes, we used to have 2, or there were 2 launched, none operational now. Gravitational spacecraft, none operational now. Those that detect particles, like for solar wind or cosmic rays, we still have 3 of those. But there are many planned. There are 14 in the planning stage. Okay, what's astronomy? That's the science of the study of the universe beyond the atmosphere of Earth. So everything else in the universe is fair game for astronomy. And obviously, astronomers largely study the universe by electromagnetic radiation, either from stars or from other bodies that reflect light from stars. Now, I only throw this one in just so that there's no confusion. Astrology is not science. Astrology is a study of sorts of how the positions of the planets and the stars at some time, at the time of a person's birth, may affect an individual personality or a future. There's no evidence to support that at all. So, how do we find our way around in the heavens from Earth? Well, we use this manufactured concept called the celestial sphere. It's sort of like an imaginary sphere, and the Earth is in the center. So it's like a globe around the Earth that is an imaginary sky. And all the stars and planets and whatever else out there are sort of plastered, positioned on that sphere. Now, we know that's not true because there's depth. It's a 3-dimensional study. But this helps us identify where things are. Because if you know where it is on the celestial sphere, you know where to point your instruments. That's the whole point of the celestial sphere. Now, this great dome of stars and other objects tend to move westward, simply because the Earth is rotating toward the east. So the sphere tends to behave as if it's moving the opposite direction, when it's actually the observer. See, the sphere is out here. with the stars out here, and the Earth is here, and it's rotating. So anybody on the surface, right, is moving that way. And that means it appears as if the sphere is moving the opposite direction. Now, we identify various points in the sphere as reference points. One is the celestial pole. The north celestial pole is, if this is north and this is south on the Earth, then this would be the south celestial pole, and this would be the north celestial pole. It's just an extension. With reference to the Earth, we're not even thinking about the tilt of the Earth. This is all with Earth as your reference. So the north celestial pole is the extension of the north axis of the Earth and where it intersects that imaginary dome. And of course, if we have this imaginary dome, we'll have Polaris right here. The North Star will be on the dome at that point. Now, there's no star for the southern celestial pole, unfortunately. But that doesn't mean we can't find out where it is. And I'm going to show you how to do that in a couple of minutes. In fact, right now. If you want to visit this website here, a YouTube video, then it gives a narration of the process for finding the south celestial pole. Now, that's not a concern for us in the northern hemisphere because we can't see it. But for those who live in the southern hemisphere, Australia, for instance, then this is important because you use the celestial pole to orient your telescope. The axis of your telescope is pointed at that pole. In the north, I always oriented my pole at the North Star. And in the south, you orient your telescope at this imaginary point in the sky. There's no star there. Well, no bright star, one that could be used as a reference point. So what you do is you look for this asterism here, the Southern Cross, right? There's the cross. And where the long cross is, you draw a line down. Just follow it down, just like that. And where it intersects with this line is the point. Now, some references say, okay, take this as one length and you go 4.5 lengths. So there's 1, 2, 3, 4.5 lengths. Will get you to that point. But I always think that's a little bit, I mean, it's open to interpretation. So they've got these 2 pointer stars that are fairly bright, and you just follow, it's like you rotate around and find these 2 pointer stars. You draw a line between them, you bisect the line, and then you draw a perpendicular until it intersects the line from the Southern Cross. And that is the celestial, the southern celestial pole. Okay. Now, if you want to verify where it is, all you need to do is set up your camera for a time lapse, and the star trail will identify exactly where it is, right there. In that case, you don't have to orient your camera. You just have to set it up to be sure that the south celestial pole is in the field of view, and you can pick up these star trails, and then you know exactly where it is. And if you set up your telescope at the same place every day or every night, night after night after night, then you can use that reference to other landmarks. And you know exactly where the pole is. Of course, if you move your telescope some other location, then you got to find it again. And this is just confirmation that the Earth is rotating. Another way of saying the Earth is rotating on its axis, well, not similar to, but as a support of Foucault's pendulum experiment. All right. Now, there's more to this that we haven't covered yet, and I've got some diagrams here. Let me keep up with my hard copy. Yes. Okay. I'm going to describe it first and then show it to you in a picture. Okay, there are planes and points. You know what a plane is? It's two-dimensional. It's like a cut. And then there are other points that are references. The ecliptic is one. The celestial equator is one. We've covered the north celestial pole, south celestial pole already. The equator is the extension of the Earth's equator. Right? So if this is the equator right here, then out here, around like that, will be the equator, the celestial equator. Now the ecliptic is represented by the apparent annual path of the sun on the celestial sphere. So it won't be the Earth's equator. Why? Because the Earth is tilted. It'll be across like that. It'll go north for a while and then south. And that ecliptic is also within plus or minus 8 degrees of the ecliptic. You'll find all the planets as well. Okay, so here's our celestial sphere in this kind of a blue hazy dome, and then this one plane cut through the Earth's equator identifies where the celestial equator is located. Right? So why do we need that celestial equator? Well, it's a reference, right? So many degrees above or so many degrees below gives you reference similar to latitude. Remember the latitude. It's similar for astronomy and the celestial sphere. And this is the ecliptic. That's what the sun follows right there. All right. Now we got another term called the equinox. There are only 2 points that are identified as equinox. Equa means equal. And you can interpret that as for the day of the year, which is identified as an equinox, the daylight and nighttime are equal lengths. And that's roughly true. There are some variations. But the equinox in terms of astronomy and the celestial sphere is the 2 points at which the ecliptic and the equator, the celestial equator, intersect. Right? The autumnal equinox, right, that occurs on our way into winter months is around September 23rd, is the point called the autumnal equinox, where the southward movement of the sun intersects with the celestial equator. 6 months later, it's on the way up on the other side. That's the vernal equinox, the spring equinox, and it occurs around March 21st. Now, what does that look like in terms of our picture? Like our celestial sphere picture. There we go. See, on this one, the sun is moving down that way. So when it intersects this ecliptic, intersects with the celestial equator, on that day, when the sun arrives at that point, is the autumnal equinox as it's on its way down. On its way up the other side is the vernal equinox. Now, the summer solstice are the other 2 points on the ecliptic. Now, they don't intersect the celestial equator. The summer solstice is that point along the ecliptic where the sun's location is the farthest north. So day after day, you tend to see the sun. If you plot the sun's position above the horizon from our location, say here in Beckley, and you start with the vernal equinox, then it will start to move northward. Day after day after day, it get higher and higher and higher. And then when it reaches the summer solstice, that's the highest. And then it starts back down. If you go day after day after day and mark at noon, then you'll be able to track the sun's movement north and south. And when it reaches its maximum point here, that's the summer solstice, farthest north. The winter solstice is on the other side when it's at its lowest. Right? So when you come around here past the autumnal equinox and you're in the winter months, then somewhere around December 20th or December 21st, the sun will be at its lowest point. Now, we name these since this whole model that we're developing was developed in the northern hemisphere. We got to name things. So the summer solstice is up here for us. For the southern hemisphere, if they had developed this model, then they would have called the winter solstice the summer solstice, because that's their summer. But we got first dibs in the northern hemisphere. So the summer solstice is the highest point for the northern hemisphere, and the lowest point for the northern hemisphere is the winter solstice. Now, here's a one that you've been introduced to on the Earth, navigation on the Earth's surface. We have a prime meridian that was established as the north-south latitude that goes from the South Pole to the North Pole through Greenwich, England. Actually, the Greenwich Observatory, right through its telescope. That's 0, prime meridian. The celestial prime meridian is a little bit different. Okay? It has a similar concept because it's from the south celestial pole to the north, right? Just draw that imaginary line along the celestial sphere. But we have to know, where is it? Right? And as it turns out, the 0 point, the celestial prime meridian, occurs at the vernal equinox. Remember, where the ecliptic of the sun rising, moving up the ecliptic, intersects the celestial sphere. The equator, excuse me, the celestial equator. At that point, that's the 0 point for astronomy. Okay. So we have special names for our navigation. Let's see, I have it here. Yeah, there's the prime meridian, half circle created by the intersection of the poles and the vernal equinox. Okay. It's a reference line, a starting line to measure celestial longitude. That is, left to right, so to speak. If we go bottom to top or top to bottom, that's called declination. And so many degrees above the celestial equator is a declination, north degrees or south degrees. So you have to specify. Is it north or south? Sometimes they'll say positive for north and negative for south. You could see that also. Right ascension is similar to longitude. only longitude doesn't say east or west of the prime meridian like we did for Earth's surface navigation. For a celestial prime meridian, we just say right ascension. And it's in units of hours, minutes, and seconds. So the right ascension is to the left of the prime meridian, or counterclockwise, so many hours, minutes, and seconds. Okay? All right. Right ascension is in degrees. And then, no, declination, excuse me. Declination is in degrees. Right ascension is in hours, minutes, and seconds. Or it could be hours with fractional hours. And that means you only have 24 of them. So you go right ascension, counterclockwise, around to the, and when you get back to your position, you'll be 24 hours. And then there's declination, north or south of the equator. Okay, so the minimum right ascension is 0 hours, and the minimum declination is 0 degrees. The maximum right ascension is 24 hours. Actually, by the time you get to 24 hours, you're going to be back to 0. And the maximum declination is either plus 90 degrees or minus 90 degrees. So if it's north, that's plus by convention. South is negative. Now, how about distances? Because if we, let me go back to our drawing. Here we go. We talked about this direction, that direction, and the one direction. That tells you where the star or the heavenly body is plastered against the celestial sphere. But the actual distance to that object could be anywhere, inside or outside what we would consider the sphere. That distance is measured by several means. It depends on where it is, how far away it is. One way to measure it is astronomical units, right? An astronomical unit is the distance, the average distance of the Earth from the sun. Astronomical unit, and we typically use that one for objects inside the solar system. Light years is a possibility. Since light travels at a constant rate in a vacuum, then as it travels through space, if you know how long it's been traveling, you know how far it's been traveling. So we just say light years, and there's a conversion from light years to astronomical units or to other forms. There are equivalences there that you can use. Parsec, that's a different one. All right, so there's astronomical unit, average distance 1.5 times 10 to the 8th kilometers. That's 1 astronomical unit. A light year is equivalent to 9.5 times 10 to the 12th kilometers. And so there's your conversion factor. A parsec is a little bit different. We have to try to wrap our brains around that one. Let's see. Yeah, this one takes a little of explaining. In words, a parsec is a distance to a star, but it's the distance, 1 parsec is the distance to a star if it is placed at such a distance that its parallax is 1 second of arc. Okay, so let's see how that works. So if here's the parallax, right? That's so many arc seconds. is that parallax. If that parallax is 1 second, then this distance from here to there is 1 parsec. And the base of the triangle is 1 astronomical unit. Right? So this is always the same. And if this parsec is 1 degree, but the star is way out here, 1 second, excuse me. If it's 1 second, then the star has to be farther away. Okay, so the closer the star, the greater the angle. Okay, let's look at this one more time. Notice that if the distance is greater, since the base of the triangle is constant, as the distance is greater, the angle becomes less. So they're inversely proportional, right? The greater the distance, the smaller the angle. And of course, this angle has to be calculated. Use a little trigonometry. So what's the distance in parsecs to Proxima Centauri? That's the nearest star to us. Right? The annual parallax of the star is 0.762 arc seconds. Right? And 1 arc second equals 1/3600th of a degree. This is the beauty of using parsec, because the equation says that the distance in parsec is equal to the inverse of parallax angle. Right? Like I said, as the distance gets greater, the angle gets smaller. So if we just take the inverse of the angle, we get the distance in parsec. So here we go. We take the inverse of, it has to be arc seconds. It has to be in seconds. Then if you take the inverse, you get parsec. 1.31 parsec. And there's a conversion for that. We showed it in the previous slide. Well, actually, we didn't show this conversion. We showed the equivalence in kilometers, but or did we? No, we didn't. We didn't. This is the conversion factor. 1 parsec equals 3.26 light years. So the star, Proxima Centauri, is actually 4.26 light years away. All right. That seems pretty simple. I mean, if you have the parallax angle, it's easy to figure the parsec, and then you can convert it into light years. Okay. How about the distance in parsec to Sirius, the brightest star in the sky? Sirius is the brightest star in the constellation of Canis Major. Canis being the Latin term for dog. It's the big dog in the sky. So that constellation has a very bright star in it. And the parallax angle is 0.376. So notice the parallax angle is less than it is for Proxima Centauri. But once we take the inverse, we find that 2.66 parsec converts to 8.67 light year. Okay? All right. The the thing about parallax is it cannot be detected with the unaided eye. The angles are just too small. You need good optics and calibrated optics with a measuring scale in the optics itself. In fact, well, I don't know exactly, but that's what I would assume. If you've ever worked with microscopes, most microscopes have an eyepiece with a calibrated etchings, marks on it. And all you have to do is use a scale and put it under the objective and correlate the markings at each power of your microscope to that scale. And then you can measure things in your field of view using the eyepiece. A similar approach is used in telescopes. But we need that approach because the angles are just so small. Friedrich Bessel, German astronomer, was the first to observe stellar parallax. This was in the early 19th century. Measuring the distance to stars works only so far, because the farther they get away, the smaller the parallax angle, right? So it only works to a certain distance. Just to give you some perspective, the closest stars are like measuring the angular size of a dime at 6 kilometers. Right? That's like 3.5 to 4 miles right in there. So the short version is only stars within about 300 light years can have their distances measured by parallax. Right? So what do? Well, we have to go to a different method. But the idea is, as you go farther and farther away from the Earth, trying to measure distances, and you use a different technique, you want those techniques to overlap so they can correlate with one another. So if your new technique, you should be able to measure things, say 100 or 200 light years away using the new technique, and then they overlap and you can compare your values to see if the new technique jives with the old. So then you can stretch out the distances on a similar scale. You don't want one method of measuring to give you different answers for the same star as the other measurement system. That just wouldn't work. I mean, it wouldn't be accepted by any scientist who had half a brain. Okay. That is an error. I just noticed that. So let's see. Oh, just a second. I might have to cut this part out. This calculation is in error, but only slightly in error, because my parallax angle here is the wrong. My parallax angle here is actually twice the true parallax angle. Parallax angle should be just right in there, half of P in this case. So if H is the distance, which won't change, 300 light years times so many meters per light year. So that's how many meters away a star can be and still produce a reliable parallax measurement. So if the base of the triangle is the diameter of Earth's orbit, that's true, 3 times 10 to the 11th, then we take the tangent of half that angle. If you've had any trigonometry, I'll just tell you, the tangent is the opposite over the opposite over adjacent. So it's this distance here, half of B divided by H is the tangent of that, of half that angle. So this is actually the theta divided by 2 is the parallax angle. Right, so you just substitute in these values. Right, so half of that is going to be half the base of the triangle, there, right there, and we determined that theta is 1.68 times 10 to the minus 9th arc seconds. But actually, the parallax angle is half of that. So I will correct that before and fix it in the blackboard. Okay, so let's start. We're going to talk about stars now. So let's start with the sun. The sun, and all stars are self-luminous spheres of hot gases. That is, they create their own energy. And they do that by nuclear reaction. Right? And they're held together by gravity. Of course, the sun is the nearest star to Earth. That's obvious. But it is huge relative to the size of the Earth, relative to the size of the gas giants. The sun is huge. Its diameter is about 100 times that of the Earth. So here's some basic facts about the sun. There's its diameter. There's its mass, 10 to the 30th kilograms, whereas the sun is 10 to the 24th kilograms. So it's 6 orders of magnitude heavier. That's quite a bit. 6 orders of magnitude is a million times heavier. The density, on average, is 1.4 grams per cubic centimeter. So that doesn't seem like a lot, does it? Well, that's because the outer layers are very tenuous gases. But once you get toward the center, the pressure there drives the density up, way up. So the average density here is sort of misleading. Luminosity, that is how many watts of energy or how many joules per second does the sun produce? 3.8 times 10 to the 26th watts. That's a lot of energy. The Earth is tilted on its axis. So it's the ecliptic plane, or the trace that the sun makes around our sky, is a certain position, but the sun is tilted by 7 degrees. So how long does it take the sun to rotate once? 25 days on average. Well, at the equator, it takes 25 days for the sun to move around. And you can time that just by watching sunspots. Right? So they watch the sunspots move across the face, and they say, okay, it's gone that many degrees in this much time. 360 degrees will be related to that, and that's 25 days. Now, everything is moving. Nothing is really standing still in the universe. It's only standing still with reference to something else. If we're moving at the same speed as something else, it appears to be standing still. I mean, that's Einstein's relativity. But relative to the center of our galaxy, the sun and all the planets with it is moving at 250 kilometers per second. Okay, so it's moving pretty quick. And there's the average distance to the Earth. Now the sun has structure. Okay, so let's look at its structure. There are 5 concentric layers that help us decide how to characterize the sun and what it's doing. Okay, so the innermost is the core. Right? You can say that about any planet also. It has a core, a center. There's the core of the sun. Right? Then out here is the radiative zone. So the core is where the nuclear reactions take place, right? Where you actually fuse hydrogen into helium. And we talked about it in the previous chapter, the mass defect. The mass defect between hydrogen on one side of the reaction and helium on the other side of the reaction is a significant amount, and that converts into energy based on Einstein's equation, E equals mc squared. So that all takes place in the core. And then this zone is the path that light has to traverse to get to the surface, right? It's got to move its way, work its way up. So it's radiated, it's absorbed, re-radiated, absorbed, re-radiated, just continuously until it reaches the surface. And then the next layer from the radiative zone is the convection zone. That's where gases are heated and they rise, right? Because they're heated, which makes them less dense, and they rise to the surface, release their heat and light, and then they cool and they go back down. So you get these convection currents, localized convection currents in that zone. The outer layer is the visible surface is called the photosphere. The radiative zone has a sublevel of convective zone. Those are the first two layers: core, radiative zone. Then the photosphere is the visible surface of the sun, and the chromosphere is a layer of very hot gases just above the photosphere. And then the outer solar atmosphere is the corona. The corona is the part that you see in a total eclipse. All right. So let's look what's happening in the photosphere. Temperature is pretty hot, 6,000 K. It's not the hottest, but it's hot enough. And it roughly has a composition of 75% hydrogen, 25% helium. But those are estimates. Less than 1%. So you'd have to take so many percent away from both of them and assign it to carbon, oxygen, nitrogen, neon, and a few others. Most of it is hydrogen and helium. It has a granular appearance. Let's see. We'll get to it in a couple of slides. Show you the granular appearance. Each of those granules is a hotspot. And that's because it's the top of a convection cell. So it comes up through the middle, and then it kind of bubbles up like one of those umbrella fountains. And then it goes back down with its neighbor. It's right up against its neighbor, and the cool of one neighbor meets the cool of the next neighbor, and they go back down until they're reheated, and they come back up through the center again. The thing about these granules is each one is about the size of Texas. So they're pretty massive. Another characteristic that's obvious is sunspots. And these occur in that layer. Let's back up. There you go. The photosphere. Right? The sunspots occur in that layer. And they break through to the chromosphere, of course. So let's get back here to sunspots. All right. The sunspots are cool regions, right? They're not part of the granular. They're special structures. And they're large patches of cool regions, so that's why they're darker. By comparison to the granular surface, they're cooler, so they appear darker, but they're still pretty hot. And they go through cycles. You have lots of sunspots for a while, and then they wane, and then they come back up, and then they wane. So they go through cycles. In the late 1600s was an unusually cold period on the Earth. And it was noticed by those who were watching the sun that there were very few sunspots. So for some reason, the appearance of sunspots is correlated to an increase in temperature on the Earth, which means what? The sun is putting out more energy. It has to be. That's the only explanation. If you have fewer sunspots, then the sun is cooler, and the Earth gets cooler because it's receiving less radiation. This time, in that time period, was called the Little Ice Age. It was cold and wet. Up to that point, they had gone through what was called the medieval warm period. For Northern Europe was very warm. It was a temperate climate, and their primary cereal grain was wheat. Okay? The Little Ice Age can roll around, and the wheat can't stand cold, wet seasons. Well, at least the wheat back then could. We have cultivars now that can do that, but back then their wheat couldn't stand it. So their wheat in these cold, wet seasons would rot. It would get moldy. So they had to switch to some other grain. So they switched to primarily oats. Oats can stand colder, wetter environment. Okay, like I said, there's a strong connection between sunspots and the global climate on Earth, which begs the question, whatever happened to man-caused global climate change? Because back in the medieval time and in this 1600s, man's not producing a lot of carbon dioxide. It's just not, doesn't happen. So how do you explain those climate changes? Well, most people who subscribe to man-caused global climate change just ignore them. Right? Let's see. What was the guy's name? He was a climatologist with the University of Pennsylvania. His name escapes me for now. But he put out this famous chart. He published a paper. And what it said was, here's time. This is the present, and this was back maybe 1000 AD. And this was global temperature. And he said, okay, we just merrily, and then here's the Industrial Revolution. Right, we start belching out smokestacks full of carbon dioxide. And he said, look at there. It just shot right up. Okay. What he, on purpose, he just threw out the medieval warm period and the Little Ice Age. Just tossed them out. And got this paper published. And he got in a world of trouble too. Not big enough trouble because people still believed it. And they just completely ignored the effect of the sun on our climate. Now, what we've learned so far about studying Venus in particular is that if you have enough carbon dioxide and other gases in your atmosphere, you can have a runaway greenhouse effect. That is possible. but the amount of carbon dioxide and other greenhouse gases in the atmosphere of the Earth are not sufficient to cause global warming on the scale that we are told will happen in the next century. It just will not happen. Of course, I won't be around to say I told you so, but if you are, be sure and remind them that their ancestors who came up with this ludicrous idea was just that. They were just total idiots. Anyway, let's get back to the topic. Close-up view of the sunspot. So this is what a sunspot looks like, and you can see the granular structure around here. Each one of these granules on average is about the size of Texas. So these sunspots are huge also. Right? Now, it looks like there's just a gaping hole in the surface of the sun. That's not a hole. It's just black because it's cooler than the surrounding area. Okay, I mentioned the sunspot cycle. On average, these appearance and disappearance and reappearance of sunspots goes through an 11-year cycle, on average, century after century, ever since we've been observing. These cycles begin with the appearance of a few sunspots near or between 30 degrees north and 30 degrees south latitude on the sun. Okay. And the number gradually increases with a maximum number in the middle of the cycle at around the 15-degree region. Right. So it starts off plus or minus 30, and then it narrows as you get more and more of them. And then the last half, that's toward about 5.5 years. Then the last half, toward the end of the 11-year cycle, they start disappearing, or you get to a new minimum. So that's your 11-year cycle. These sunspots also show magnetic polarity. So what that means is, and don't ask me how they measure that, it's complicated. The 11-year cycle from minimum to maximum back to minimum, when it comes back down numbers of sunspots and time. So we go from 0 to 11 years. Okay. So you go up and then you go back down. But you have say a plus polarity here and a minus polarity there in the sunspots. So they go back up again for another 11 years. Now they're back to the same polarity they were when they started. So actually the cycle is a 22-year cycle. The 11-year sunspot cycle is superimposed upon a 22-year magnetic cycle. All right, other features. Flares and prominences. The flares are explosive events, very bright, that occur on the sun's surface. And a flare is just that. It's like lighting off a flare, and it just goes like that, blasts into space. That's a flare. Prominences are filaments of solar gases that arc from one point on the sun to another point. And they're actually following magnetic lines of force on the sun. So those charged particles in the filaments, the gases there, are following those lines. Sometimes those prominences become so big that they erupt. They break loose their magnetic anchors and they turn into flares. So sometimes they are related. But they can go out hundreds of thousands of kilometers, both prominences and flares. They're best observed for most people during solar eclipse. The sun is so bright that it's hard to see them, any detail around the outer edge of the sun, because that's where they, against the blackness of space, it should be easier to see them. But the glare of the sun is just so great that you have your telescope set up there. You have to put a filter on your telescope to keep it from burning your eye out or overexposing your film or whatever the case may be. So for most people, you have to wait for a solar eclipse in order to see them. But solar telescopes have a built-in eclipse disk in their optical path, and it covers up the sun. So they can observe these things anytime they want. And they put that type of optic in satellites that are designed to observe the sun day in and day out, year after year. Now, if these prominences develop into a flare and they're aimed at the sun, of course, if they're on the outer rim, they're aimed at right angles to our orbit. But if one erupts from the surface toward us, then we get a massive flux of charged particles fired at the Earth. And what that can do is it can disrupt or damage our power grid or satellites in orbit. So what we need is a way to predict that a flare is going to occur. So that's one of the purposes of this constellation of satellites that are in sun orbit and aimed at the sun. They're scattered around the sun so they can watch. And they can watch and see a prominence coming around before we can see it, coming around, and then we can prepare ourselves for the, actually there's a term for that. Let's see, am I going to talk about it in a second? It's called a coronal mass ejection. Let's see. Yeah, we'll get to it, but I'll tell you now. A coronal mass ejection. When that happens, those charged particles are flying at us at very high speeds, up to 10 or 12% of the speed of light, So it takes them a while to get here. But if we have notice from our stationed satellites that it's going to happen, what we can do is we can power down satellites so that their electronics and protected, actually. What we try to do is build a satellite so it's protected, but we power them down so that there won't be any spurious voltage spikes that can get through, like we break connections electronically within the satellite. We also can anticipate the effect of these coronal mass ejections on our power grid. You've learned with electricity that moving charged particles will induce a current in a conductor. Remember that? Well, these charged particles are flying in, and what they're going to do is they're going to strike our magnetic umbrella, right? Our magnetic umbrella. But when they do that, they are accelerated around the Earth, and as they're doing that, they emit a magnetic pulse. Even from that height, that magnetic pulse is sufficient to overload our power grids. And with these long cables that are stretched out across the countryside, remember, you can get a pulse in a wire that short, but when the wire is miles long, you get a huge electrical pulse. So sometimes it's advantageous just to power down the grid until the pulse passes and then power it back up. So you can tell all your customers, you know, we're going to have a planned power outage due to this coronal mass ejection, and just shut everything down, and when it passes, bring everything back up. Now, this electromagnetic pulse can also occur from human efforts. Every time an atomic bomb is detonated in the atmosphere, it produces an electromagnetic pulse, an EMP. And that's one of the bad things about an atomic bomb. I mean, the blast is bad enough, but you don't have to blast your enemy with atomic weapons. You just detonate an atomic weapon at 100 kilometers up, and it blankets the whole country with this electromagnetic pulse. And if they don't see it coming, if we don't see it coming, say we're the enemy, then it can shut down our power grid. Okay, back to the sun. So here's a prominence that's developing into a flare, right? It goes from one point to the other, but notice here it's already broken loose. And this is a pretty big one, right? Fortunately, though, it's aimed away from us. So this corona comes from the word crown. And if you've ever seen a corona in a total eclipse, you'll see the way it moves, it looks like it's got spikes on a crown. Okay, this is the sun. Excuse me, this is the sun's outer atmosphere. And these temperatures can be up to 1,000,000 Kelvin. All right, remember what temperature is. Temperature is a measure of the average kinetic energy of the molecules in the substance. So these temperatures can be 1,000,000 K, but the gas is so thin that there's not a lot of total energy there by comparison. If the gas were at 1 atmosphere, yeah, 1,000,000 K would be a huge amount of energy. But since it's at a fraction of an atmosphere, then you have high kinetic energy, but very few gas atoms. See the difference there? All right. So here's the coronal mass ejection I was talking about. So we don't have to spend a lot of time there. It's a massive burst of charged particles. Right? And they come flying at the Earth or at any planet or satellite or whatever in their way, and they can do some damage. Okay. Now, the coronal mass ejections are a one-time event, and then they're gone. And then another one could happen. But a continuous flow of charged particles at these high temperatures are streaming out from the sun in all directions. This is the solar wind. Those ions, protons, electrons, whatever, are given sufficient energy to escape the sun's gravity, right? If they don't have enough energy, they can't get away. So you know they've got to have a lot of energy to get away from the sun's gravity. So the solar wind keeps going out into the outer solar system, and it reaches a point where it becomes so tenuous that we can virtually ignore it. I mean, it's on the level of interstellar space. It's at the same level there. At that point, we call that the heliopause. It's like it doesn't get any bigger. It's paused. It's at least 50 astronomical units. But actually, we've got spacecraft out there. The Voyager 1 and 2 craft have actually measured the heliopause to go out between 90 and 120 astronomical units. So on average, right, 100, 105 or thereabouts, we can say is the actual heliopause. We didn't know that before the Voyagers got out there and measured it. All right. Most of the material in the heliosphere, that's as long as you have the solar wind and can measure it, that's the heliosphere. Most of that material originates from the sun. Very little from other sources. Okay, let's look at the sun's interior, because that's where all this energy is coming from. The interior of the sun is so hot that individual atoms cannot exist. Right? There's enough energy for the electrons and the atoms to be stripped away from each atom. They're free. The electrons are free. The nuclei of the atoms are free of each other. And they're very high speed, high energy, and colliding, of course. They form a fourth type of matter that we call the plasma. And a plasma is simply a high temperature ionized gas. So that's what you've got inside the sun. A plasma. So at the center of the sun, the temperature is estimated at 15 million K. So the corona is about 1 million K, but in the center of the sun, it's about 15 million K. And the density goes up to 150 grams per cubic centimeter. Right? So under that pressure, the gravitational force, the gases are compressed to 150 grams per cubic centimeter. So that's pretty high. So about 25% of the sun is considered part of the core. And that's where hydrogen is consumed to form helium. You need just the right conditions. Outside of the core, temperature decreases, the density decreases. And the energy produced in the core starts to make its way to the surface. All right. This fusion reaction in the core takes place, we believe, as part of a three-step process called the proton-proton chain. Now, this is a proposition that seems most reasonable based on the evidence, right? So there's no way we can know for sure because we can't sample it under those conditions. Sometimes we can recreate some of those conditions on Earth, but not exactly the way it is in the sun. And I'll just comment, the light that's produced, right? It's a photon. Remember that? Photons. We were talking about light. It takes the photon some time to travel to the surface. Some estimates are as little as 4,000 years. Other estimates up to 1 million years. Right? So nobody really knows. So here's the proton-proton chain. First, you get one proton and another proton to come together under this enormous temperature and pressure, and they form a deuterium nucleus, right? The electrons are not there. So how does it do that? Remember when we talked about nuclear reactions? What happens to a proton? Let's back up. What happens to a neutron? If a neutron loses an electron, right, then it produces a proton, right? Let's see. Did I do that right? Oh, we don't put charges. Sorry. Proton. So the proton has one here, and it has one there. And this has one here and 0 there, right? This is the atomic number. Neutron's not a proton, so it has 0 atomic number. So this is the negative atomic number for electron and a positive atomic number for the proton. So you add those two together, you get 0. You add these two together, you get 1. Okay. But if we take a proton and it emits a positron, that is an electron with a positive charge, like that, then what do you get? Well, we need a neutron. So if you add this one together with that one, you get 1. This one to that one, you get 1. So during the first step, you get a deuterium nucleus with a proton and a neutron and 1 positron with a, let's see, some light emitted. Then you take this, we're still in a chain, so you take this product and you smack it together with another proton. And now you get a helium isotope, right? Because helium has 2 protons. And it has a mass number of 3, has 2 protons and 1 neutron. And it gives off, I know what this one is. This is a gamma ray. Gives off gamma radiation. Then you take 2 of these helium nuclei, right? Smack them together, and now you keep 2 of these protons and the 2 neutrons. So that gives you a helium nucleus, and then you get 2 protons regenerated. Okay, so that's the 3-step process. And let's see, there's 1 proton becomes a neutron. There you go. And the net reaction is 4 protons, right? If we go back, 1, 2, 3. And actually there's, right, you need 2 of these here. So that means you need 2 of those and 2 of those. So it's 2 of these and 2 of those, right? If we're going to balance our equations and add them together, then you have to have 2 of the B's. Okay, let me get back over here. There we go. So overall reaction is 4 hydrogen nuclei yields 1 helium and 2 positrons plus 2 gamma rays plus 2, I think that's ultraviolet, plus a lot of energy. And the amount of energy is simply the conversion of mass, the mass defect from this side to that side, converts into energy by Einstein's equation. So let's look at this. Every second, 6 times 10 to the 11th kilograms of hydrogen is converted to 5.96 times 10 to the 11th kilograms of helium. So there's our mass defect. The difference between this number and that number is the amount of mass that was lost in the process. Okay? Every second. Right? So 4 times 10 to the 9th kilograms of mass becomes energy every second. And you can use E equals mc squared to calculate 3.59 times 10 to the 26 joules per second is produced by thermonuclear reactions in the sun. All right? So that's a lot of energy. But let's put it in perspective. In the United States, in 2020, we consume 9.81 times 10 to the 19th joules per year. So every second, the sun produces enough energy to sustain the United States at its current level for 3.67 million years. That's a long time. But let's not be selfish. That's just the United States. Let's take the world. The world energy demand is 7.77 times 10 to the 20th joules per year by the year 2040. Right? So it's increasing. And by the year 2040, the world will be demanding, this is projection, will be demanding 10 to the 20th joules. So if we take that same amount of energy and spread it over the world at this level, the sun could sustain the world at that level of consumption for 462,000 years. The problem is the Earth doesn't get all that energy, right? We looked at that before, the solar constant for the Earth, because that energy goes off in all directions. But it was an interesting calculation to do. Okay, here's the end of the story on this slide is the total mass of hydrogen remaining in the sun is about 10 to the 30th kilograms. At this rate of consumption, the sun could continue to radiate energy by hydrogen fusion for another 5 billion years. Right? So it's not going to burn out anytime soon. Right, so there's our solar constant again. On every square meter of the Earth, we receive on average, every second, 1.4 times 10 to the 3rd watts. That's known as the solar constant. But we've already demonstrated that it's not constant. It goes up and down. That's an average over many, many years. And even a very small variation in that amount, plus or minus 0.5%, has disastrous effects on the planet's living systems. It changes the climate by just that little variation. So I'll say it again. Global climate change blamed on humans is a wild goose chase. It's a farce. Okay, remember the sun was estimated to be 75% hydrogen and 25% helium at this point, with some lesser amounts. That's characteristic of most stars. Regardless of what type of star it is, this composition is relatively constant. Okay, and they're producing energy the same way that the sun is. With surface temperatures, though, of these stars, they range, a fairly wide range. What did we say? The Earth's photosphere was in the neighborhood of 6,000 K. They can range between 1,500 and 50,000 K in the photosphere of the stars. Okay, and we use that information. How do we know that? Well, let's see. Am I getting ahead of myself? Let's see. Yeah, I'm a little ahead of myself. But the stars do vary. So some stars will look sort of reddish. They're the low temperature stars. Some will look yellowish, like our star. Some will look white or even blue. Those are the very high temperature stars. These temperatures, temperature correlation with color is an outgrowth of work that was done by Gustav Kirchhoff. And the research comes under the heading of black body radiation. So in a nutshell, in the short version, if you take a solid chunk of, say, carbon, and you do this in an oxygen-deprived atmosphere where it won't burn. So you just keep heating it up and it won't burn at all. It's just a compressed chunk of carbon, and you heat it up. It's black to start with. And as you heat it up, it starts to glow. At first, it's kind of reddish, and then it goes reddish orange, and then it goes yellowish, and eventually you can make it white hot. Temperature, temperature, temperature increase. So there's the correlation between color, which in astronomical terms would be a measurement of its spectrum. Its electromagnetic spectrum is related to the color, and that is correlated to temperature. And that's how they tell the temperature of the photosphere of a star, based upon its electromagnetic spectrum. This guy right here, Gustav Kirchhoff, also did work with electricity. And if you were taking electricity in a physics course, you would hear of Kirchhoff again. He's got what's called Kirchhoff's laws. We won't go into those right now. It's just an interesting fact. Okay. So the mass of most stars can vary as much as 8/100ths of the Earth's size to 100 times or more solar masses. Most range between 1/2 and 5 solar masses. Right? So this is the absolute range, and this is most stars. Right? One solar mass, which is a measure of masses that is convenient, right? We know what the sun weighs, so it's more convenient size measure to say, all right, that star is twice solar mass, 2 times the solar mass. So if the sun's producing all this energy inside, it produces pressure, right? All that energy makes things heat up faster and builds up pressure. It's pushing out because of that that energy, right? What keeps it from flying apart? Right? There's outward pressure from thermal and radiation produced in the core, right? Gravity is holding it together. So there's a balancing act between outward forces from inside, thermal and radiation forces, and then there's gravity holding it down. It has to be balanced. Otherwise, if one of them wins out, say if gravity wins, then the star shrinks, perhaps until another balance is reestablished. Or if the thermal radiation wins, then it'll expand until it reaches a point where the thermal radiation is diffuse enough to where gravity can hold on to it. So those are two balancing forces. And when you reach a balance point, we say that the two forces are in hydrostatic equilibrium. That seems odd to me. I understand static. It's the appearance of no change. But hydrostatic? Hydro in my mind means water. But be that as it may, those are the terms that are used. Hydrostatic equilibrium is a star that doesn't expand or contract. It's balancing those forces. Okay. Now the sun is all by its lonesome. It's just one star, and that's it. No other companion stars anywhere. That's unusual. Most stars are part of multiple star systems. Right? Binary stars would just be two stars that rotate around their center of mass. Remember when we were discussing Pluto and Charon? They rotate around their center of mass. Same thing can happen with stars. So two stars can rotate around. If they're the same size, the center of rotation will be right in the middle. If one is bigger than the other, then the center of rotation will be closer to the bigger one. This is most stars. Most stars are binaries. Some are trinary or more. Our nearest neighbor, Alpha Centauri, is actually three stars together, gravitationally locked in orbit around their common center of mass. Okay. There's some speculation that Jupiter could possibly have become a star, except it just doesn't have enough mass, right? And that may be what happens to some star systems. Binary system, they have a planet out around Jupiter, Saturn, in that area, that's bigger than Jupiter. And it's big enough to where it collapses into a small star, and then it orbits with its companion. Okay, what's a constellation? Well, constellation is actually an imaginary grouping of stars. They have to be bright enough and prominent enough that ancients, in particular, would look at the night sky and they'd imagine some figure, a person from mythology or an animal, usually, but it could be something else that is represented by the arrangement of those stars. They form a recognizable pattern from Earth. Now that doesn't mean any of those stars are at the same distance from each other. Usually not. But from Earth, they appear in that pattern. And like I said before, most of them were given names in ancient times. And it also depends on what culture is being investigated, because different cultures have different constellations. Right? They might see the same set of stars, but they see a different image superimposed on those stars. Right? And like I said, there's no physical significance to that pattern at all. They're not related to each other, gravitationally, distance, whatever. But they are useful for finding your way around in the sky, looking for different things. So the constellations were standardized. In 1927, the International Astronomical Union set boundaries for 88 constellations, and that divides the entire night sky, northern and southern hemisphere. Those are all agreed upon. So we know that within this region, if it's a constellation, say Orion, then this pattern covers that region, and anything outside that doesn't belong to Orion. Okay. Now, of course, as the Earth rotates, they tend to move across the sky, but also as the Earth revolves around the sun, we start looking at different parts of the sky at different seasons. So the prominent constellations in our sky are different for each part of the season of the Earth's travel in 1 year. We might call those annual cycles of movement. Now there's another. Constellations represent animals, people, some things. Asterisms are simply groups of stars that are usually part of constellations. They don't have to be, but most of them are. They're already part of a parent constellation. An asterism is just a collection of prominent stars that form a pattern that's useful. One of the most well-known is the Big Dipper and the Little Dipper. The Big Dipper is part of Ursa Major. Ursa means bear. So the Big Bear is this one right here. So there's the Big Dipper right there, like that. There you see, like that. The tail here. And the Little Dipper is here, part of Ursa Minor, or the Little Bear has a Little Dipper. The nice thing about that is, for us in the Northern Hemisphere, is that these two stars in the Big Dipper, on the bowl of the Big Dipper, point toward, in general, toward this region at the tip of the tail of Ursa Minor and the handle of Little Dipper. That is Polaris. That's where the North Celestial Pole is fixed at this present time. Remember, because of precession, that will change over time. But it'll take thousands of years to do it, so don't worry. Another example is the summer triangle. Right? Do I have a picture? Yeah, here's a picture. In this case, the summer triangle actually has 3 stars in it, 1 star from each of these 3 constellations. Right? So the Big Dipper and Little Dipper occurred within a constellation. The summer triangle is a triplet of stars that occur in 3 different constellations. Right? This Vega star is in Lyra, which is, Lyra is like a lyre, a harp. This star Altair is in the constellation Aquila, and Aquila is an eagle. And this one, Deneb, is part of the Actually, that's the tail of Cygnus the swan, right? Swans have long necks. So here's the long neck of the swan. There's at the end of its tail, and these are its wings. So these three, this summer triangle, is, as you might guess, visible in the summer months. All right. So I've already talked about that, so I'm not going to belabor that point. All right, let's talk about celestial magnitude. What do we mean by that? Well, man has been looking at the sky for thousands of years. And in ancient Greece, there was a Greek astronomer, mathematician, Hipparchus. And he was a dedicated observer of the stars. He cataloged many of them, up 800 of them. And he located them on maps, identified them, and produced this star catalog in 129 BC with these 800 stars. The thing about it was, he assigned a magnitude or a brightness to the stars. Now, this was apparent. This is what they appeared on Earth to be, this brightness. This is the apparent magnitude as seen from Earth. You know, where we're going is the fact that if you hold two lights at two distances, right? If I hold a flashlight right up here in my eyes, it seems really bright. But if I look at a street light, 2 or 3 light poles away, it's very dim. But if I held that street light right up here at the same distance, it would be brighter than the flashlight. So that's where we're headed. This is the apparent magnitude of the stars. And he assigned first magnitude stars were the brightest thing that he could identify. And the 6th magnitude stars were just barely visible to the unaided eye. And then everything else was subdivided in 2, 3, 4, 5s in between. Okay? We still use Hipparchus scale, only slightly modified. Now, instead of estimating by visual observation of the stars, we use instruments that are less prone to interpretation. They will actually measure the intensity of light coming from the star and compare it to the actual intensity of other stars. And now we can measure apparent magnitudes of many, many more stars, because now we can use optical instruments to measure much dimmer stars, and we can assign brightness to brighter objects like planets and the sun. So the modern scale, since we have quantified the intensity, now we can say a difference of 5 magnitudes between 1 and 6, for instance, is a difference in represents a difference of 100 in absolute intensity of the brightness. To put that in perspective, a first magnitude star appears 100 times brighter than a 6th magnitude star. So what does that mean? If we go from 1 to 6, that's 5 steps. 1 to 2, 3, 4, 5, 6. 5 steps. So each step should be represented by 20 times. So second magnitude should be 20 times as bright as the first magnitude. 20 times dimmer. Or if we go to 6th to 5th, it should be 20 times brighter than 6th magnitude. Okay. So let's go back to the Big Dipper. 6 of the 7 stars of the Big Dipper have an apparent magnitude of 2. So these in the tail, which doesn't appear that way by this drawing, but this one, that one, and these 3 are all the same magnitude, magnitude 2. And the 7th one, this one right here, is magnitude 3. So these stars are 20 times brighter than that one at the base of the handle. We can measure the apparent magnitude of other objects in the sky. So the sun is magnitude minus 27. Okay, right? But we just extend further. So the smaller the number, the brighter the object. The full moon is minus 13. Its apparent magnitude. Right? The sun is very bright, but if we put the moon at the same distance as the sun, it would be imperceptible. It would be so weak. Venus is the brightest planet at a minus 4. And that's on the average. Because if you observe Venus month after month after month, you'll see a change in its brightness. Sirius is the brightest star. Right? We measured that or interpreted that earlier as 8.7 light years away from us, and it's a magnitude minus 1. So I can imagine that Hipparchus saw Sirius. It was the brightest star in the sky, and he called it 1. But now that we quantify things, we find that visual interpretation of brightness is not quite accurate enough. So with our new system that was established and agreed upon, now that we've assigned Sirius a magnitude of minus 1. Sirius, just for your information, is in the constellation Canis Major. I think I said that earlier. Canis means dog. So it's the big dog. So there's a big dog and there's a little dog, like there's a big bear and a little bear. That's why we call it the dog star. Okay, now absolute magnitude. The distance from the Earth does matter. Right? The absolute magnitude, it decreases by the square of the distance. So something that's 2 times further away from us will have its apparent magnitude decreased by 4 times. That's the inverse square. So the absolute magnitude of a star is standardized as the brightness of the star if it were 10 parsecs from the Earth, 32.6 light years. I don't know why they picked that distance. Probably because some stars are so bright, you got to get them that far away in order to get them in a reasonable scale. So that's the standard. What would the brightness of the star be if it were at 10 parsecs from the Earth, 32.6 light years? So that being the case, the sun's absolute magnitude is plus 5 at that distance. Now, what's so great about knowing apparent versus absolute magnitude, right? Yeah. Well, if you know the absolute magnitude and the apparent magnitude, then you can use the inverse square law because it has in the formula a distance measurement, the square of the distance. If you know those 2 values, then you can calculate the distance to that star. So we're hunting for a method that will allow us to infer the absolute magnitude of the star, because we can measure the apparent magnitude. What we want to know is, what's the absolute magnitude? Okay? That's not an easy task. We'll talk about that a little more later. But for now, we want to look at stars and the types of stars. We want to classify stars. And we use this diagram, the Hertzsprung-Russell diagram, to plot the absolute magnitude of the stars versus their temperature. Okay, when we can do that, then we find that most stars become brighter as they get hotter. It's not just the temperature that changes as they get hotter, but they also get brighter as they get hotter. These particular stars will plot in a chart on a narrow band in the middle. And I'll show you that in just a second. So the hottest stars are generally the brightest stars, and the coolest ones are the red ones are the least bright. Obviously, there are exceptions, but they're important exceptions, and they help us to understand how our stars develop. So let's look at that diagram. Right. Notice one thing about this chart. Which way did the temperature scale go? Temperature scale goes from right to left. So the temperature of these stars is increasing from right to left, from red to blue. Red, orange, yellow, blue. Now this central group of stars here follows that pattern. The absolute magnitude here increases as the temperature increases. So as we go from right to left, we go up. So we're increasing magnitude as we increase temperature. And this is another way of expressing it, luminosity. Right? Either way works. There are some stars that do not follow that pattern. Okay? This is called the main sequence. Stars that fall upon the main sequence, and the sun is one of them, right here. It's slightly yellowish. And right here, see 6,000 K, that's the temperature for the sun, the photosphere. So what about the stars that are not on the main sequence? Several types do not follow the sequence. Red giants, for instance. Red giants are very large stars that are cool, but they're very bright, simply because they are bigger. They give off more light, even though they are reddish, right? So let's go back. These are red giants. Betelgeuse and Antares are both red giants, and they have lower temperatures, but they're very bright. I think probably because of their size. The very brightest ones are red supergiants. They are massive stars. Now, on the other end of the scale are white dwarfs. These stars are very hot, but they're very dim because they're very small. Interestingly enough, when we analyze the spectrum of these stars, no matter what their color is, we find that they contain the same elements as in our solar system. Right? I mentioned earlier, the same mix of hydrogen and helium and some minor elements. There are variations, and that depends on the temperature of the stars, which is good because this pattern of absorption lines, remember, if the star is emitting certain wavelengths of light, and we see missing places in there, dark lines, then we can associate those dark lines with elements in the atmosphere of the star. But also we can identify those patterns with not only the composition, but the surface temperature of the star. Lots of information can be gained. Now, you don't have to remember this, but there's a law, Stefan Boltzmann Law, that allows scientists, astronomers to infer from the surface temperature the temperature of the star is related to the emission of radiation from the star. And the important thing to take away from this is that if you treat the star like a black body, that is, it gets more and more yellow, white, blue as the temperature increases, the radiation effect there, the amount of radiation that comes out of that star is proportional to the fourth power of the temperature. So the radiation the amount of radiation that's given off is proportional to T to the fourth. Right? It's not T squared, it's not T to the third, it's T to the fourth. Now, you can see this trend, you can see this phenomenon anytime you have your car parked outside at night and the temperature dips, say in the late winter or late fall. You have a very, actually in the middle of winter is good too. If the sky is completely black and the air temperature outside is above freezing, 34, 35 degrees, you go out the next morning and you'll find ice on your windshield. How does that happen? The temperature was greater than freezing. Right here. Your windshield acts like a black body radiating energy. And it radiates energy at this rate, T to the fourth. Right? So your windshield is compared to the blackness of space, there's a huge difference between the temperature of your windshield and the blackness of space. It radiates that energy very efficiently. And as it radiates the energy, any water, any moisture at the surface of the glass is frozen. Check it out. Next time you have a clear black sky outside, go see if you got ice on your windshield. And it helps if the humidity is high also. Well, let's move on. Spectral classes. All right. So we've identified the relationship between absolute magnitude and temperature. Now we're going to group the stars into classes. Right? So here's the class across the top. O, B, A, F, G, K, M. Notice that as you go from O to M, you're becoming more red. Right? Start off blue. Some of the blues are O's, some of the blues are B's. Then you get to A's where you're starting to get white. F's are definitely white. G's, you're starting to get a little yellow. K's are definitely yellow and some orange. And then M's are all reds. And this spectral class incorporates these stars that are off the main sequence as well. Right? So this Deneb or Betelgeuse or Procyon B, they're all in those classes simply based upon their spectral analysis. Now, how do you remember those right? Well, a mnemonic helps, right? Oh, be a fine girl or guy, kiss me. That's one way, right? So O, B, A, F, G, K, M, classes from blue to red. Or another one you might try is, oh boy, a failing grade kills me. That's a mnemonic device to help you remember the sequence of letters. Okay, so the sun is, we might classify as main sequence, G class. So here it is in the main sequence, and it's a G class, okay, based upon its spectral analysis. And here it is down here, 6,000 K. It's just barely starting to develop a yellow tinge. Whereas Sirius, where's Sirius? Sirius. Here it is. Sirius is a main sequence star, class A. Now, if you use this stuff every day, a colleague of yours or someone you're communicating with in the discipline would say something like main sequence class B, and you instantly know exactly how it's characterized. Like Bellatrix would be main sequence class B. It would have a surface temperature of approximately 25,000 K, and you'd know that. Okay. Astronomers have found that most stars are small, cool, class M, like these down here. Also called red dwarfs. Apparently, they have just enough solar mass to ignite a nuclear reaction, but it's not very energetic. Their core is small. They're putting out low amounts of energy. So at the surface, the temperature is kind of low as stars go. That's where most stars end up, in that class. And they're very dim, right? So it's hard to find them, right? You need a good telescope and good instruments to find those stars. Proxima Centauri is that type, a red dwarf. So what's in the interstellar medium between the stars? Well, believe it or not, there's lots of gas and there's lots of dust distributed among the stars. It's very tenuous, but sometimes as you're looking through great distance, it looks thicker than it would appear, right? It's like a compression. You're compressing light coming from a depth into a plane, so it appears more substantial than it is, but it's still important. These gases are about the same composition as stars, 75% hydrogen, 25% helium, and traces of other elements, right? Looks familiar, doesn't it? So it might lead one to guess that maybe stars are formed from these interstellar gases. Right? These collections that we can identify with limits to them are called nebulae. The obvious conclusion is that nebulae gases are not evenly distributed throughout the universe. They gather together in clumps, some very large areas of gas and dust. Nebulae are the concentrations. They're very cool. They're dense. Of course, compared to empty space, they would be considered dense. And they're cool because they don't generate their own energy. They're not luminous on their own. Right? So there are two major types of nebulae, the bright nebulae and the dark nebulae. The bright nebulae are those that have a nearby star from which they can receive energy and reflect it or re-radiate energy. Those are bright nebulae. The dark nebulae are those that have gas and dust that are obscuring light from the background. Now, the bright nebulae also come in two types. Emission nebulae, in which the energy from nearby stars is sufficient to excite primarily the hydrogen gas in them, which re-radiates. That's a process called fluorescence. You see that in your light bulbs. Some light bulbs, compact fluorescent bulbs, they use that process. Energy is absorbed by a gas and then re-radiated. Those are emission nebulae. Then you have reflection nebulae. In these, the dust in the nebula reflects the light energy that's falling upon it and scatters the light. And they generally give off a blue color. Now, the emission nebulae can be the whole gamut because re-radiation or fluorescence can occur at any wavelength. But reflection nebulae generally occurs in the blue region simply because of the size of the dust particles. We see that in our Earth's atmosphere. The size of the molecules and the dust in the atmosphere tend to reflect blue better than any other wavelength of light. Let's see. We'll talk about planetary nebulae in a minute. Okay, here's an example of an emission nebula. The Orion, the Great Nebula in Orion. Okay, here it is. The Frenchman Messier identified and numbered many objects in space, and this one he gave a number of 42. The Orion Nebula. Yes, the Orion Nebula, excuse me. This is an emission nebula. There's a very hot star, either in the gas cloud or behind it, which is causing it to fluoresce. And this is the Orion Nebula. So remember the constellation Orion. This helps you to locate things. And Orion is very recognizable in the sky. I think it's an autumn constellation. Notice here these three stars together, very prominent. That's known as the belt of Orion. These are part of his two legs. These are his shoulders. These out here are part of his shield and his arm up here with a sword in it. But there are other features of the Orion Nebula that are very interesting things to look at. We'll talk about them in a minute. Also, you might notice that these prominent stars that are labeled around here occur at these different distances. Betelgeuse is 643 light years. Mesa is 1.1. I think that's probably, that can't be 1.1. This must be European notation. That's 1,100 light years. Remember, in Europe, they use a period for a comma. And for the decimal point, they use a comma. And we do just the opposite. So that's 1,100 light years. And there's 772 light years. So these stars just happen to fall into that appearance of neighborhood, but they're really not. And this is the Great Nebula in Orion, right here. Right? If you have a nice telescope and you can take a picture. In fact, these types of pictures require time lapse, time extended exposure, because the brightness is so low that it takes a while to expose them. So what we used to do in the old days when you used film was you would have your camera in there and you would open it, expose the film, and you would have a device in your hand to where you could keep your telescope tracked exactly on that object. And you have a separate scope on the outside that you use your guide scope. And you would have that guide scope aimed at a prominent star, and you would just sit there and you would adjust it and keep it on that star with as little movement as possible, so that it would track the nebula and give you a long exposure, picking up lots of light. Nowadays, with electronic devices, cameras, you take multiple exposures. You just go click, 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 and you just keep click, click, click. And then you put them together into a single exposure inside your computer. That also brings out more detail. Okay, dark nebulae, where they obstruct light coming from behind in the background. This is usually caused by interstellar dust. There's several out there. The most famous of these also occurs in Orion. It's called the Horsehead Nebula. So let's see if I got a picture of it here. Okay, here's another version of Orion. And there's the one we just looked at, the Great Nebula in Orion. And the Horsehead is right over here by the base of the belt. Okay, and here's a bigger picture of it. Right, so that's why they call it the Horsehead. This dark nebula is obscuring light from the background. There are other features here, like the Flame Nebula. There's this huge collection of gas here, and another one here. There's a Witch Head Nebula over here, which is an Emission Nebula. But I don't have a close-up of that one. And talk a little bit about the evolution of stars. In other words, how does the star change over time? How is it born? What stages does it is it progressing through to its ultimate demise? First of all, no matter what the star's size to begin with, or how it gets started, how it ends, these are theories, models, if you will, of the star's evolution based upon some limited evidence that we have from this spectral record that we've discussed so far. Main sequence, non-main sequence, and so forth. So we're going to have to take the astronomers and the physicists at their word when they say this is what they think happens to these stars. All right, so we're going to start with low mass stars. In this case, the star begins to form, and some of these characteristics are common to low mass and high mass stars. Stars begin to form as interstellar material. And this class of star is usually the H variety, I think. Oh, excuse me. No, not the H variety. What am I thinking of? The stellar material, which is mostly hydrogen. I can't even remember my own abbreviations. They begin with hydrogen, and this interstellar material has helium in it also. Remember, 75% hydrogen, 25% helium. This is called accretion, when it starts to gather together. So why would it gather together? Well, ultimately, it's due to gravity. They start attracting one another. But there are other forces involved to get them started. There's some evidence that electrostatics plays a part. When they're rubbing against each other, they transfer electrons, they produce uneven distribution of positive and negative charges, and they attract one another. It's a possibility. Gravity, of course, and sometimes they get a push from the outside. The solar wind from a nearby star, or especially an exploding star, will produce a shock pulse that travels through the gas cloud and causes compression, a gathering together of material. And when that happens, you not only get the compression, but you get a shear, a spin is introduced. Those are some possibilities for the beginning part of accretion. There I mentioned gravitational effects, radiation pressure from nearby stars, shock waves. Okay, I mentioned that one. I left out electrostatics. There may or may not be evidence for that. I'm just speculating with that one. What forms initially is what called a protostar. That is, the material has gathered together and condensed, and the temperature starts to rise. That's what happens when gases compress. The temperature goes up. But the temperature is not high enough yet for nuclear fusion to start. So that's why we call it a protostar. That is the beginning of proto. The composition of the star will be similar to the composition of the nebula, mostly hydrogen and helium. Now, why would it be the same in the star as it is in the nebula, right? Hydrogen is lighter than helium, isn't it? Well, we go back to Galileo for this one. What's the equivalence principle? The equivalence principle says it doesn't matter what the mass of the object is, under the same gravitational field, they accelerate at the same rate. Same thing for hydrogen and helium. Under the gravitational influence of this protostar, as they start to coalesce, the hydrogen and the helium fall in at the same rate. It's no different for atoms as it is for bowling balls. Okay, temperature's rising, continues to rise. Eventually, the temperature rises high enough that we start to get fusion. Hydrogen produces helium and generates an outpouring of energy based upon that overall reaction we mentioned before, the proton-proton chain. Okay, when thermonuclear fusion starts, the star is born. So here we have in this lower right-hand corner, interstellar gases make a protostar. And the reason it looks a little red is it's just getting hot. It gets hot because the gases are condensing. And when you compress gas, it gets hot. So eventually, these low-mass stars condense onto the main sequence. And that's where it stays for a while. For our sun, it's been there for about 5 billion years, and it's got another 5 billion years of energy left. So that's when it's said to move on to the HR main sequence. And this position is determined by the temperature and its brightness, consequently its brightness. So ultimately, its position on the main sequence depends upon the star's mass at the beginning. Now, this is for stars that head for the main sequence. They end up on the main sequence. And we're not talking about stars that are off the main sequence. They're special cases. So these low mass stars end up on the main sequence, and our star, the sun, is considered a low mass star. Here we go. Bigger picture of it. So it goes along for however long it takes to burn up its energy, and then it goes to the next phase. Now, the period of time that the star stays where it is on the main sequence depends and varies from star to star, varies widely. Like I said before, a star such as our sun will be there for 10 billion years. A very, very low mass star will stay on the sequence for trillions of years. Now, why would that be? Low mass stars burn, so to speak, they burn their fuel much more slowly because their internal temperatures are much lower. So they're high enough to start fusion, but the mass isn't large enough to compress more of the star into the core. So they have a very small core, and the hydrogen outside the core is feeding into the core gradually. There's some mixing. It's not static. And they eventually burn up all their fuel, but it takes a very, very long time. On the other side, now we talked about low mass stars up to this point, but by comparison, a high mass star burns its fuel very fast because it has its larger mass. It compresses to a larger core, which means that nuclear fusion occurs for more of the mass, and it burns through its fuel very fast. Maybe only a few million years, and it's gone. It goes to the next step. So the core begins to contract even further as it converts hydrogen to helium. And as it contracts, the extra heat eventually causes fusion of the hydrogen in the surrounding shell to proceed more rapidly. So what we're talking about here is a fight between the internal pressure and gravity. So the hydrostatic equilibrium is not permanent. So as the fuel starts to get burned out toward the end of the star's life, it can't maintain the internal pressure. So gravity starts to win, and the gravity causes it to contract. And as it contracts, you get more pressure, higher temperatures, and it burns more fuel. So it stabilizes for a while, and it begins to contract more. And eventually, the fuel runs out, or almost runs out. And for the low mass star, now it's not producing enough energy to combat gravity. I'm getting ahead of myself. I apologize. As the star heats up, as it contracts, it heats up. Okay, now it's got the internal pressure wins, and it starts to expand. Well, there's a fight between the internal pressure and the gravity, so it gets to a point. It expands into a red giant, but then it starts to contract again, and it expands and contracts. So it turns into a variable. And at this point, it moves off the main sequence. Why? Because the main sequence is a correlation between temperature and magnitude. And if that correlation doesn't match the main sequence, it's off. So that's what happens. The absolute magnitude increases as it expands, but the temperature doesn't increase. In fact, the temperature may decrease some, and it may move backwards a little bit. Okay, so when it's in the red giant phase, it will swell, gets bigger. It may, a star the size of our sun may expand as big as the orbit of Mercury and Venus. But it's still getting hotter as the core tends to now don't ask me why this happens. I'd like to know myself. This red giant phase, actually, it's a shell of gas that's moving out, right? Expanding from the core. The core is still there, and it's working away at what it's got, but it's running out of hydrogen. So now it starts to convert helium, and eventually helium will end up as carbon. So we're actually transforming nuclear transformation into heavier elements. So in normal stars, you can go up to carbon, sometimes even up to neon. Nucleosynthesis, one word for it. Nuclear transmutation is another. So that's how we start to get heavier elements. The larger the star is to start with, the more gravity, the more compression, the higher temperatures you get in the core. And when the hydrogen runs out, you start to manufacture higher and higher mass elements. And what we do is, in normal stars, we can get up to iron. And that's where it stops. It gets no higher than iron. I've got a, let's see. I know it's in here somewhere. Yeah, it's several slides down the road. But I'll explain why it stops at iron. So hold that thought, and we'll get to it in a couple of slides. So goes to this red giant phase, and then it moves on as the star's temperature and brightness start to vary. And for a short time, relatively speaking, the star begins to pulse in a way. It gets brighter, and then it gets dimmer, and brighter and dimmer. This is called an intrinsic variable. And its temperature increases, and it gets brighter as well. So this move sort of parallels the main sequence. As it tends to shrink and swell, then it shows a change in brightness. This intrinsic variable as opposed to an extrinsic variable. An extrinsic variable is variable based upon light being blocked by something orbiting in front of it. So a companion, maybe a dark, we'll talk about it later, a brown star, or maybe even a large planet could cause variability in its emissions. That's an extrinsic variable. Intrinsic means it's variable because of something inside it is happening. Now, planetary nebula. After the variable star phase, the star becomes extremely unstable, and the outer layers of the star get blown away. It's not technically speaking, it's not an explosion, but the outer layers do get blown away and form what's called a planetary nebula. So we made this donut here to represent the planetary nebula, and it gets the magnitude decreases, but the temperature is still pretty high. Doesn't have anything to do with planets. It's just based upon the early photographs that were taken. Were very fuzzy, and they tended to look like planets. This material diffuses into space and is out there to be recompressed into new stars at some point in the future. It's available. Here's a very famous one, and it's a beautiful planetary nebula. So here's the outer layer of gases that are blown away, even some in here that are blown away. And notice that in the center is a white dwarf. A white dwarf is left behind for low mass stars when they reach this phase. Okay? So what is a white dwarf? It's the remaining core of the star. It's what's left behind. There's no more thermonuclear reaction. None whatsoever. And it starts off as a white dwarf, but it gradually cools. Slowly cools, radiating whatever energy is left behind. And there's sufficient energy there to give us this white color. So it's still pretty hot. It's just there's no thermonuclear reaction going on. The star is essentially dead. Right? And loses a lot of brightness. Even though the temperature is up here, the brightness is very low. Another interesting fact is that a single teaspoon of this white dwarf would weigh 5 metric tons. That's 5,000 kilograms. It's very, very dense. Why? Because there's no radiation coming from the inside, no new radiation pressure. So gravity is winning. Gravity wins and just crushes it. So here's an example. A binary star, Sirius. The dog star, remember? It is a binary star. Sirius A, this big one, is a Class A main sequence star. Right? That puts it, let's see, in the neighborhood of well, it's a little bit brighter than the sun. I mean, higher in temperature than the sun. Well, a little bit by several thousand degrees, several thousand K. Then this companion star, Sirius B, is a white dwarf. Okay, they determine it's a white dwarf based upon its luminosity and its spectral characteristics. But that begs the question, where's the nebula? Right? If that's a white dwarf and it's part of the low mass evolution, where's the nebula? Well, possibility is that the nebula's there. It's just with this bright star in front of it, you can't see it. Okay? That's probably there. The other possibility is that it's blown out way beyond these two stars. It's just completely gone. but I don't know for sure. Now, I mentioned brown dwarfs. If a protostar doesn't have enough mass to trigger the fusion reactions, then it never makes it to a star. So technically, it's not a star. It never did make it there. The only reason it has any color at all is by compression of the gases. Okay, it might also be called a failed star. Just never did make it. It's a little bit bigger than, say, Jupiter, but it's not big enough to be a star. And they're very dim. So they went unnoticed for a long time, decades. In 1996, the first brown dwarf was discovered. And so far, we've identified about 100 of them. Okay, so this is just a review of a low-mass star. It goes through the phase, interstellar gas, protostar, triggers thermonuclear reaction, and stays on the main sequence for a long time. Billions of years, maybe even trillions. And then toward the end of its life, it swells to a red giant, becomes a variable star, and then blows off its outer shell. Becomes a planetary nebula with a white dwarf in its center. That's the low mass evolution of a star. Now, there are other observed phenomena from stars that are very interesting. And the theory is that this one, called a nova, is a white dwarf that temporarily and suddenly increases in brightness. So why would it do that? Because white dwarfs, they don't generate any of their own energy. They're just supposed to gradually be cooling, get cooler, cooler. But sometimes a white dwarf will flash. Nova means, in Latin, a new star. But it's not a star. So why is it doing this? Well, the theory is that new matter, fresh matter, is falling onto the white dwarf from a companion. And when it hits the surface, the temperature then is high enough, right? Because it's a white dwarf, it's very hot. There's enough energy in that white dwarf to initiate a flash of nuclear reaction on its surface. So it doesn't last very long, but it does get bright. Now, how does a high mass star? Well, first of all, we've already learned that high mass stars don't last very long. High mass stars tend to move off the main sequence as red giants, and they eventually explode as a type 2 supernova. Now, that doesn't mean a lot right now, but keep that in mind, and we'll talk about it some more. The end result is that the supernova, the explosion, leaves behind some of the star, but a large part of it is blasted out into space. And what's left behind is one of two possibilities: either a neutron star or a black hole. So we need to define what those terms are. Before we do, let's look at the sequence, right? Here's your interstellar gas, right? Has to be a really large cloud, correct? Light years on order, and just accretes into a protostar. This protostar is massive, it's huge, right? Forms a high mass star, and it burns very quickly, right? Because it has a very large core due to increased pressure. and it needs to generate a lot of energy to resist that collapse. So it reaches hydrostatic equilibrium at a large state, but with a huge core pressing against all that gravity. So it burns out fast. And then it eventually expands into a red giant and proceeds actually, this explosion phase, it's a matter of minutes. It happens so fast and leaves behind a neutron star or a black hole. All right, so let's talk about that in detail a little more. I've already said large materials thrown off. So that's where it creates, it's a large enough mass so that before it explodes, it can produce iron. It can go up to iron. But we need heavier elements because they're there. They're on the periodic table. We need those heavy elements. It's believed that this explosion provides just the conditions to produce the heavy elements. So how does it happen? Well, there are two types of supernova. Type 1, which we haven't explained yet, results from the destruction of a white dwarf, which contains a carbon-oxygen core primarily, by the additional capture of material from a companion star. And if it's just a little bit of material, it makes that nova. And it will happen periodically, actually. But if the companion star is close enough and it donates enough material to the white dwarf, then it may initiate nuclear fusion again on a massive scale. So the material that is donated by the companion star must exceed 1.4 times solar masses. Right? So if the mass of the star then increases to that level, it'll reignite fusion, but it's very unstable and causes a supernova. The star just completely blows. A type 2 is developed from a red supergiant, from a massive star that at the end of its life. And at its very core, it's basically iron. And when it does that, it doesn't have enough internal pressure from nuclear fusion to resist gravity. So what happens is this red giant, let's see if we get over here, this red giant collapses. Once the iron level reaches a certain point, nuclear fusion can't maintain, and it collapses in just a few minutes. And when it does, it rebounds. It collapses under enormous pressure, and when it hits bottom, it just, it's a rebound explosion. And what it leaves behind is either a neutron star or a black hole, and that depends on the mass. Okay, how do we tell them apart? Right? We have this theory about why each one happens. Right? We discussed that in the previous slide. Type 1s are white dwarfs that accumulate enough mass to restart the nuclear process, but that's so unstable that they just blow up. Type 2s, collapsing of the iron core of a red supergiant. Okay, so how do we tell them apart? Well, as a matter of fact, and the spectral signature of each one is radically different. Type 1 supernova don't have a hydrogen spectrum, and they do not emit radio waves when they explode. Right? But type 2s, instead, the spectral line shows carbon from the white dwarf. So that's a clue. Type 2s do have the hydrogen spectral lines because they've still got a lot of hydrogen in their atmospheres, and they emit radio waves. Right? So here's an example of a type 2 supernova. This one was first spotted by Chinese astronomers in 1054. Okay? And remember, wasn't the 1056 was the Battle of Hastings, when the Normans crossed the English Channel and took over England. And I think they saw this supernova as an omen. Anyway, so it's been known for a while, and it's gradually been changing over the centuries. So it didn't always look like this. This is a current photograph of the Crab Nebula. Where is the Crab Nebula? Right? If you want to look at it yourself, some of these nebulae can be seen if you have a nice dark sky and a good telescope. You might be able to see some of them. Some of them, to get this kind of detail, you need a timed exposure. It needs to go for a while to pick up enough light. But if you find the constellation of Taurus, Taurus the bull, you find the head here and the horns here. So on the southern horn, right out here toward the tip, is M1, the Messier Catalog first description. So the Frenchman Messier, this was the first one he described, number 1. There are other interesting features here. Asterism, actually. These are the Hyades, Hyades. They're star groups that are part of the head of the bull. Aldebaran is one of them, a fairly bright one. And then over here is Messier's 45, M45, which are the Pleiades. The Pleiades are also called the Seven Sisters. So there's 7 stars in here that are bright enough to be part of the asterism. And these are the 7 sisters. And here's Orion. See, so Taurus is very close to Orion. Just keep going north like that. And if you have the head of Orion and his shoulders, they sort of point toward the Crab Nebula. The Crab Nebula is one of only 10 supernovae that have been recorded in the Milky Way galaxy. Right? You would think with as many stars in the Milky Way, we'll talk about that in a minute, that you'd have more of those. But none of them were from direct observation. I mean, somebody didn't actually see the flash and so forth, at least not in recorded history. All we see is the aftermath in the Milky Way. Okay, I'm coming up with a better one. The supernova was reported to have occurred in 1054. But the direct observation was not detailed. Let's put it that way. It is reported that during the first 2 weeks of the supernova, the night sky was bright enough to read by. Okay. So we haven't had any direct observations in modern times of any supernova. We've only seen the remnants of them, but we do have written records of this particular one. So what was left behind, right? Was it a black hole or was it the neutron star? In fact, it was a neutron star. So it's 2,000 parsecs away, or 6,500 light years. And there's a neutron star there at the center of the crab. In fact, this neutron star is a pulsar. And I'm going to define that for you also. But you can tell from the name that it pulses. But we're going to describe why it does. However, there was one supernova that was observed, direct observation, in 1987, and it happened in the Large Magellanic Cloud, which is a galaxy. It's not a cloud, it's a galaxy, but it can only be seen from the southern hemisphere. And it was seen at its very beginning when it flashed, and it's been observed ever since. The estimate of its distance, its absolute magnitude, are that it produced the same amount of brightness as 100 million of our suns for several months. So it went on for a long time. These supernovae happen very quickly, but they can continue to radiate lots of energy for a long time. It was discovered in February 23rd, 87. Now I've got an animated GIF here of that observation later on in its life. And these images were compiled. It wasn't just one telescope. There were several, and we put it together in a form that was carries lots of information with it. So the Hubble telescope, Chandra was a telescope, and ALMA telescopes. These all were combined to give you this animated GIF. So that's what it would look like. Notice that it's got a ring structure, right? But it's also got this halo out here. Okay, so where is it located? Well, here's the Large Magellanic Cloud in the southern hemisphere skies, and here's a small Magellanic Cloud. So inside this one, this particular video, the first video, zooms in on the remnants of that supernova. So it's just going to zoom in and show you where it is. And then the second one is a time lapse between 1994, right? So that's 7 years after it was first observed, through 2016. It shows how it changed. So let's do the first one. Okay, so we zoomed in on it so we know where it is. Now let's see what it looks like close up, time lapse. So we did notice some changes. Oops. Let's go to the next slide. There we go. So let's talk about nucleosynthesis, making heavier elements. The energy required and the neutrons present in normal star evolution, whether it's small or large stars, is insufficient to make elements larger than iron. So we can make anything up to iron in normal stars. But in order to make anything heavier than that, you need a huge number of neutrons. Why? Because the neutrons don't have a charge. And they can penetrate to the nucleus of these heavier elements and combine to make larger nuclei. That's not to say that protons don't contribute, but if you have a large amount of neutron density in and around these elements, you stand a better chance of making heavier elements. And that's why we need the higher energies and the higher neutron flux to produce heavier elements past iron. Remember this graph that came in an earlier chapter, earlier discussion of nuclear reactions. When we talked about fission and fusion, the relative stability of the nucleus, if it's on this side of the curve, then it can move up the curve because that's more stable. And it does so by fission. Or if it comes from lower down, hydrogen, tritium, lithium, helium, neon, it gains stability by moving up the curve, which means fusion. It becomes heavier and heavier. All right. So under normal conditions of a star development, iron is the most stable element, right, on this chart. Iron normally will not fuse, it will not split. It won't fission, it won't fuse. But if we have high enough neutron density, high enough temperatures and pressures, then you can force iron and some of these other elements to fuse into heavier elements. And we can move right on down the scale, backwards as it were. From fission, we turn it into fusion. Okay, so let's go back and look at what's a neutron star. When the nuclear fuel of a red giant runs out, this cataclysmic collapse I described earlier, as the red giant collapses, can form a neutron star, approximately 20 kilometers in diameter. So why would it collapse now? Because the hydrostatic equilibrium is now unbalanced and favors gravity because the nuclear fusion is running out. And as the outer layers collapse, they bounce off that rigid inner core, which is predominantly iron, and then expand into space. And that leaves behind the core, the neutron star. Okay? This occurs over a matter of minutes. But it takes a while to brighten up to its maximum luminosity. Okay? It's called a neutron star because the electrons and the protons under this enormous pressure combine to form neutrons. Remember on our nuclear reaction, if you get an electron combined with a proton, on the nuclear scale, you get a neutron. It's the reverse of the disintegration of a neutron into a proton and a beta particle, which is an electron. Okay. So nothing's left behind but basically neutrons. Well, the interesting thing about a neutron is they're neutral. So since they're neutral, if there's any gravity there at all, they can be compressed and there's no charge, no repulsive charge to resist that compression. So neutron stars are extremely dense. A teaspoon would weigh 1 billion tons. Okay? We haven't talked about black holes yet, but we will. So what else can the neutron star do? Well, remember conservation of angular momentum. Stars are usually spinning, right, in the beginning. They may be slow, they may be fast, whatever. But as they collapse, the momentum has to be conserved. So as the neutron star collapses, it has to spin faster because its radius is less. Remember, radius times angular velocity gives you angular momentum. So as it collapses, it has to spin faster and faster. So the small size means very rapid spinning. And remember, this is a type 2 supernova. And one of its characteristics is radio wave emission. And it's going to emit radio waves, but depending on how it's oriented toward us, as it spins, it comes around and the radio waves are directed toward us and then not, and directed toward us and then not. So it seems to pulse because it's spinning. Pulsars can be, many of them have been observed in the order of seconds as their periods. So they're really spinning fast. I mean, 4 seconds is fast enough for a neutron star, you would think, but they can spin around in 3/100ths of a second, a complete rotation. Now, another reason that they pulse is not just the spin, but the fact that their spin axis is one thing and their magnetic axis is another. So they got a magnetic axis this way. So as they're spinning this way, they could be perfectly normal to our line of sight and spinning. But their magnetic axis is off center, so it comes around and we see it. And then it comes around again, we see it again. So that's another reason that they pulse. And this is an artist's idea. Magnetic field lines here. This is the spin axis, but this is the magnetic axis. So as it spins around, this beam of radiation aims at us and then away, and aims at us away. It just continues to do that. Okay. Oh, also, as the pulsar ages, this period of rotation tends to get longer and longer. So what that tells me is that as it rotates, it's dissipating energy, right? Because angular momentum also means that it has a certain amount of energy. And the only way it can slow down, because it's got kinetic energy from spinning, the only way it can slow down is to dissipate that energy. So the energy is probably being thrown off in these these radio beams, right? Light has energy, so it's giving off that light, and it's losing energy, which means it has to slow down. Okay. How do we get this information? Well, we need radio telescopes, those that are designed to pick up radio waves of whatever frequency we desire. And the larger the telescope, the better the image. Right? We can see smaller things, or we can separate 2 stars that are close together better with a larger telescope. Well, there's a physical limit to how big a telescope can be made. Right? I think the biggest one in the world is the radio telescope in Puerto Rico at Arecibo. That's a single dish that fills an entire crater. But there are other techniques that can be used. And in this case, This is called the Very Large Array. It's located in New Mexico. And these dishes are pointed at the same point in the sky, and they're receiving radio emissions from whatever source. And due to the fact that they're separated by these distances, means that they simulate a disk that's as big as the array. But it takes a little electronic and mathematical wizardry to make sense of the signals that they're getting. So these signals are combined in such a way that they interfere with one another. This is called interferometry. And eventually you can put together a picture in the computer of the patch of sky that you're observing in greater detail than if you looked at it with one telescope only. So here's our Crab Nebula again, and it has a neutron star in it, which is a pulsar that spins 30 times a second. It's really fast. And it definitely emits radio waves, but it also occasionally emits pulses of visible light. And my guess is that the intensity of the magnetic field in that neutron star, coupled with the emissions of radio waves, are interacting with the gas cloud, and it's causing it to fluoresce periodically, pulsing in the visible wavelengths. Now, if it's a neutron star, okay, but it could be a black hole. So what's required to make a black hole? Well, first of all, what is a black hole? Black holes were originally theoretical. They were predicted by Einstein's theory of general relativity. In other words, a black hole is an object. As far as we know, it was originally a star that is so massive that light cannot escape from it. That's why it's black. Remember when we talked about the bending of light due to large mass? Well, if you got a star here like that, and remember the, let's see, who was it? Shoot, my mind's gone blank. The expedition for the eclipse, where the star was observed, the light bent here, like that, around the sun. Well, if the star is bigger, you get more bend. And if the star is big enough, the light comes in and it cannot escape. So there's no light coming from the black hole, right? The gravity is just too high. The light will not move. So gravity finally won. It's the ultimate winner. It can capture light. So what's the mass limit? What's required to make a black hole? It's believed, and this is probably a good bit of theory based upon the general theory of general relativity. When the supernova explodes, what does it leave behind? It leaves behind a certain amount of mass. Well, if the mass is big enough, it can collapse into this structure. It can go beyond the neutron star, and the gravity will crush it down and capture light as well as mass. And it's believed that 3 times the mass of the sun is the lower limit. So if we leave behind from a supernova 3 times the mass of the sun, it should theoretically collapse into a black hole. Now, the theory also is that the star's mass collapses down to a singularity. So a singularity is the physics expression of a mathematical point. It has no width, it has no height, it has no depth. It's a single point. I don't know if that's true or not. That's the theory. But when you hear the term singularity, that's what they're talking about. All right. So let's say for argument's sake that the black hole is not rotating. The rotation would add a complication to it. So for theoretical purposes, there is the singularity is here, represented by a dot. And then there is a distance from that dot called the event horizon at a given radius, depending upon the original mass of the star. So if it's larger mass, then this R value should be greater, should be increased. So what happens at this distance on the event horizon? That's the point at which neither matter nor light can escape. Anything that crosses that boundary is lost forever. You'll never see it again. If the mass of the black hole were equal to the present mass of the sun, which seems kind of funny because we just said it's got to be 3 times that to make the black hole. But this is a theoretical calculation. So if the black hole were produced and it had the mass of the sun, then this R value would be 2.9 kilometers. So it's pretty small, actually. And I don't know how to calculate that value. So I just assume that if it were actually 3 solar masses, then this value would be a lot bigger. So that begs the question, if the black hole is black, how do we know it's there? Right? Our only source of information is light. If light can't escape, how do we know they're there? Right? Because the event horizon is a one-way boundary. Nothing gets out. Anything that reaches that point goes in and stays in. All right, so what's the question? Well, one way to detect them is there's a spot in space and you don't see a star there, right? There's no light, you can't see it. But there is electromagnetic radiation that's coming from around it. Why? Because as matter approaches the event horizon, gravity causes it to accelerate. An acceleration of any charged particle, of which most matter has some, an acceleration of charged particles under those forces causes the emission of X-rays. Right? So we can detect a phenomenon around a space that we think has a black hole by emission of X-rays. This happens in what's called the accretion disk. Now they say it's a disk, but I'm not so sure. Probably it's a disk simply because most black holes are not stationary. In fact, I would say all of them are moving. They rotate. So that rotational effect tends to flatten things out into a disk. So as gases are captured into that disk, the accretion disk, they emit X-rays. Okay, and remember, when something gets closer to the source of the gravity, the potential energy decreases. Remember, potential energy, when we were talking about classical mechanics, as you move up away from the Earth, you have higher potential energy because of the gravitational field you're in. you input energy and you moved higher in that gravitational field. Well, the reverse happens. If something heads toward the center of the gravitational field, then its energy is converted into kinetic energy. So that kinetic energy means it has to accelerate to get there. So accelerating charged particles in that environment produces X-rays. Okay, here's a class O star and a black hole called Cygnus X1, I believe. Cygnus X1. Yes, Cygnus. There, Cygnus X1. And its companion star is losing mass to this black hole. And when the gas reaches the accretion disk, it begins to accelerate, it loses potential energy, and some of that energy is converted into X-rays. So that's one way that we presume, one clue that there is a black hole there. Now there's another class of black hole that has just in recent decades been identified and fairly well proven, accepted by the physics community, called the supermassive black hole. Now we're getting extreme, really extreme in mass. These objects are believed to exist at the center of every galaxy, because galaxies are big collections of stars and lots of mass, particularly toward the center. They tend to accrete mass, stars, so forth, toward the center. And when they do that, when they combine, they eventually reach, in fact, I'm speculating here, they don't actually know how the supermassive black hole forms. But if you get enough mass, then you can start a black hole. And one thing about black holes, they tend to have voracious appetites. They consume mass like there's no tomorrow. It's believed that a supermassive black hole exists at the center of our Milky Way galaxy. So we've abbreviated it SMBH. I can't eat right now.
I'll just set it in my.
Okay. Now, in order to be a supermassive black hole, it's got to be huge. And I'm not talking tens of solar masses. I'm talking about hundreds of thousands to billions of solar masses. These things are monsters. Okay, these were first hypothesized in 1971. So that's what, 40 years. The hypothesis was proposed by Lyndon Bell and Rees, two astronomers, English astronomers. And their work in looking at radio galaxies, the ones that were very strong radio emitters, some galaxies are like that. They proposed that there might be supermassive black holes at the center of these galaxies. And actually, those radio galaxies are probably very far away. Be that as it may, the radio evidence in 1974 pointed to the likelihood of just such an object in the Milky Way. Initial estimates were of 1 million times the mass of our sun. Okay, so we're starting to develop a theory about supermassive black holes. Confirmation was obtained eventually. See, these are speculations. Confirmation, evidence, was obtained from the orbital trajectories of nearby stars. Okay, so stars that were orbiting the center of the galaxy, we were able to image them and measure them over time, their movement over time, and they were moving really fast. Their trajectories suggested that the only way that these stars could move that fast in their orbit was if they were orbiting a mass of 1,000,000 times the mass of the sun. Actually, that was the first estimate. Based on this work, the estimate now was increased to 4.6 million solar masses. So that's closer to reality. So there's the Milky Way galaxy, I think. Yeah. And we're looking here, it's dark because we're looking through the plane of the galaxy, and there's a lot of gas there and it's obscuring things. But they were able to do some radio astronomy on the center of the galaxy located at this arrow. Why did they use radio? Because radio waves can penetrate dust, whereas light cannot. Now, just look at it, it's dark because visible light doesn't make it through. But radio waves were used, and they were able to do the research based upon that. A Nobel Prize was actually awarded to 3 scientists. One was with the Max Planck Institute in Germany, Genzel, and the other 2 were Americans. Let's see. I thought there were 3 of them. Andrea Ghez of UCLA. There's a 3rd one I know. But these 2 groups, Genzel and Ghez, actually gathered the experimental data, the observations that were used to do the calculations. And I think the 3rd was more theoretical. The 3rd person was theoretical. That's probably why I left it out. This is a photograph on the right. This is in the constellation of Sagittarius. They have this section of sky down here blown up, and it's believed that right there on that cross is the black hole. And measurements were taken over a long period of time. Once they located it in near infrared, they found that near infrared would penetrate this dust cloud. So they used that because with higher frequencies, infrared, visible, on up, you get more detail. So they used the highest frequency they could use and still observe. So they had to settle for near infrared. And trajectories of these stars around that position were determined to indicate the presence of a supermassive black hole. Okay. We've talked about high mass and low mass stars. We're just going to list some comparative statements about those. Let's see. Here we go. High mass and low mass stars form initially in the same manner, right? Up to the protostar and igniting nuclear reactions. High mass stars are hotter and brighter, generally speaking, than low mass stars. High mass stars move on to the main sequence at higher points. That is because they're hotter they're further up the curve. Let's see if I'm going this direction. Oh, this direction. Further up the curve, yes. Higher temperature, higher brightness. But high mass stars don't stay on the main sequence as long as low mass stars because of their higher rate of fuel consumption. So we've also learned that the fate, the evolution and fate of a star depends upon its initial mass. That's the single most important determining factor for the life cycle of a star, is its initial mass. But the final mass of the star is what's left over after its last gasp. So if it ejects material, that determines what's going to happen to it. Whether it's in actually planetary nebulae are a low mass star consequence. And supernova remnants are more like new nebula, the large irregular nebula, like the Crab Nebula, for instance. Okay, so here it is in one collection point, the final mass of the object. This is not the initial mass, the final mass, what's left over at the end of the life of the star. If it's less than 1/100th of a mass of the sun, you're going to end up with a planet or a moon. Right. So what that means is it never made it to be a star. It's just not big enough. 0.01 to 0.07 mass, it never made it to a star either. But it's a brown dwarf. In other words, it will radiate some energy based upon collapse and heating, or it might even reflect energy from other stars. Between 0.08 and 1.4, the leftover from the life of the star, you're going to end up with a white dwarf. Anything over 1.4, remember, a white dwarf that collects some more matter from a companion, if it exceeds 1.4, then it's going to supernova, right? It's going to explode. 1.5 to 3, without that collection, you end up with a neutron star. Well, you would end up with a neutron star here also. If that white dwarf collected a lot of material beyond 1.4 masses, then the consequence would be, well, if it collected actually much more than 1.4, because it's going to blow off a bunch of it. So what's left over? If it's 1.5 to 3 masses of the sun, you get a neutron star. But if what's left over is greater than 3 masses, you'll get a black hole. And these are general parameters that have been deduced from multiple sources. All right, let's talk about galaxies. All right, talk about stars up to this point, but there's more structure to the universe than just stars or nebulae. A galaxy is a very large collection of stars, gas, and dust. And it's all held together by mutual gravity. And it's believed that the universe is organized around the structure of the galaxy. In other words, for example, where would we find the Earth and its sun? Right. I'm going to steal some of my own thunder. The Milky Way is believed to be a spiral galaxy. So it's got a central hub, and then it's got arms radiating out like that. Okay? And they're thicker in here than they are out there. Stars are very close together in here, which means that there's a lot of energy there, too much energy. It would be energy, the night sky would just be a blanket of white if we had a planet in this area. So the sun is actually way out here on one of these arms, where the density of stars is a lot less. It's more hospitable to life. It's a good thing too. So the galaxies are organized. They organize the universe for us. And in fact, galaxies were believed to have started very early on in the development of the universe. We'll talk about that more in just a minute. So, how many stars are there in the Milky Way? They're only estimates. We estimate between 100 and 200 billion stars are in the Milky Way. And that's fairly common for galaxies in that neighborhood. Other estimates from the Hubble Space Telescope and the New Horizons spacecraft that just flew by Pluto, they think that the estimate is probably closer to the 200 billion mark. We're going to find out more, though. The story is not finished. It hadn't been written. When the James Webb Telescope is established at its L2 Lagrange point and starts operating, then it will be able to see structures and perhaps even stars through the obscured dust and whatever in the galaxies in the universe. It may be able to observe more stars. So that estimate will probably change once the Webb telescope is in place and operating. So how do we classify galaxies? Right? Because they're not all the same. This is one type, a spiral galaxy. Well, Edwin Hubble proposed a classification based upon their photographic record. He said there are four types. There's an elliptical galaxy. There's the normal spiral. There's the barred spiral. And there's everything else, irregulars. Okay? So this simple classification scheme, based upon photography, with care for orientation of the galaxy to the observer. Because if our galaxy is observed by some other civilization, but they're out here, the galaxy's on this plane, they'll just see a sliver, right? They won't see the spiral. So we have to take other factors into consideration in judging whether it is a, say, an elliptical galaxy or maybe a spiral. Or it might even be a barred spiral, but if you're looking at it on the flat plane, like Saturn's rings, when they're turned that way, there's not much you can see. So how do you know it's one or the other? Okay, so there are a lot of variables in there that have to be considered, not just the photographic record. Okay. Elliptical galaxies. They're either spherical or elliptical. In other words, an ellipse would be like this, right? And it's probably spread out towards you as well, so it's sort of flattened. Or it could be a spherical galaxy. It could be like this, in which case it's just like it's round all around. Doesn't have any arms that are identifiable like a spiral galaxy does. So these are examples of elliptical galaxies here and here. And you have other examples, right? That one looks like some kind of a spiral. Okay. A normal spiral. Two definable regions. Right? You have the central nuclear bulge, right? This is the nucleus of the galaxy. It's more or less spherical in shape. Lots of stars. They're very tightly bunched together. That would not be a good place to have your planet. And then extending out from the bulge is a curved spiral. Now the spiral, it doesn't just have these spindly arms. You know, it has stars scattered out here. They tend to thin out as you get toward the edge of the spiral. For example, that's the Milky Way, we think. Now, Charles Messier, I mentioned him before, created a catalog of 104 objects that he observed in the sky. And he thought that they were, I don't know what he thought they were, whether they were nebulae or galaxies, but some of them are nebulas, some of them are asterisms that are very close together, and some of them are galaxies. And occasionally we still use those references, but that's not the final word on classification and numbering system for galaxies. Right? Now we use the NGC system, the New Galactic Catalog. And it's just N, capital NGC with numbers after it. Right? Updates have been performed. The latest was completed in 2017 and retained this NGC designation. Right? So here's the Andromeda Galaxy. M31 in Messier's catalog. So Andromeda is the only, let's see, one of only 3 galaxies that can be observed with the naked eye. There are the small Magellanic Cloud, the large Magellanic Cloud in the southern hemisphere, and Andromeda in the northern hemisphere. Right? The only reason that you can see this other galaxy is because this is a photograph. Okay, here's another one, the Whirlpool Galaxy. This is a normal spiral. See, there's a central bulge, and these are the arms radiating out like that. It looks like it's interacting with another galaxy, which I believe it is. This is the Sombrero Galaxy, for obvious reasons. It looks like a hat. Okay. Now, examples of barred spirals. They have 2 broad expansions called bars radiating out like this. And then from there, the spirals. Okay. Here's an example. This is the spiral galaxy NGC 1300. So it doesn't have a Messier number. This is a New Galactic Catalog number. These are irregular galaxies. Best examples are Large Magellanic Cloud and Small Magellanic Cloud. All right. Several 100,000 galaxies have been identified. That's a lot. And each one Each one contains upwards of 200 billion. Wait a minute. There several 100,000 have been identified, but it's estimated that there are 200 billion galaxies in the universe, in the part of the universe that we can see. Okay, in order of abundance, so far, of the ones that we've identified, the elliptical galaxies tend to be the majority. Then comes the normal spiral galaxy, and they outnumbered the bar spiral galaxies. Then last are the irregular galaxies. They're only about 3% of the total. Now, it's important to recognize that the ratio of these galaxies to one to another may be influenced by their distance from Earth. Remember, light takes time to get to Earth from these galaxies. And based on how long it takes to get to us, we're looking at the galaxy the way it was 100 million years ago, or 1 billion years ago, or 10 billion years ago, right? So it's not like that anymore. We can be pretty sure of that, but that's the way it was then. So this mix is more than likely influenced by how old is the observation, how far away is the galaxy that we observe. Right? So the nearest galaxy to the Milky Way is the Sagittarius dwarf. It's about 50,000 light years. And you can only see it through a telescope. That's why we didn't know it was there for so long. Somebody had to actually be looking for it. Discovered in 1994. Okay, it's an elliptical galaxy, and it's believed to be gravitationally locked to the Milky Way, being pulled in. Eventually, it will be consumed by the Milky Way because it's much smaller and gravity wins. Distance from the Earth doesn't seem to influence the mix of galactic types. That's an important point, because if the galactic type were only seen at certain distances, then we could say something about, evolution of the galaxies. But the mix tends to be the same no matter how far away they are. So these formations, these mixes of galaxies were established early on, and they've been there for a very long time. The second nearest galaxy to the Milky Way is the Large Magellanic Cloud at 160,000 light years. The Small Magellanic Cloud is about 200,000 light years away. Right, so we're getting farther out, farther out. Andromeda, the one that we can see with the naked eye. I've done that. I've seen it in the night sky when it was dark enough. You can see that. It's huge. And it's in the constellation of Andromeda. It is about 2.2. That should be million light years. Another correction. Give me a second. Let's see. Galaxy distances. Here it is. Million light years. If that galaxy were within 2.2 light years from us, it would probably swallow us up. It's so big. Right, and I already mentioned that before. These are the only 3 galaxies that are visible with the naked eye. We can see the Milky Way in the night sky, right? And it was called the Milky Way because it looked like spilled milk on a clear night. Okay. the unaided eye can, on a very, very dark night, can pick out about 6,000 stars. And all those stars are in the Milky Way, right? Because you can't see individual stars in faraway galaxies. The resolution of the eye just isn't good enough. All right. So this is what the Milky Way galaxy would look like if we were above or below it. You'd see the arms trailing out, and we'd be out here somewhere in this arm. This is what it would look like on edge. The distance to the sun from the center is about 28,000 light years. And the width is about 2,000 light years. So 28,000 light years between the bulge and where we are in the spiral arm, out here somewhere. This is another infrared picture of what we think the Milky Way would look like. Now, there are other features to the Milky Way galaxy that we've been able to identify. They're called globular clusters. They're relatively dense clusters of stars in the neighborhood of 10,000 stars each. They're not separate galaxies. They're too close for that. Right? It was discovered that these stars form a halo around the outside of the Milky Way. Right? And Harlow Shapley in 1917 mapped the location of 93 of the known globular clusters at that time. And he determined their distances and their direction. And he found that these clusters were not clustered around our solar system, but they were clustered around the galaxy. They were about 28,000 light years away. Does that look familiar? 28,000 light years from the center of the galaxy to the Milky Way galaxy to our planet or our sun. So off in the direction of Sagittarius, right, which is toward the center of the galaxy, is where those globular clusters are located. So they are centered around the central bulge of the galaxy. Okay, so just to reiterate, dimensions of the Milky Way galaxy, 100,000 light years in diameter, okay, 2,000 light years in thickness of the disk. The bulge, though, is 20,000 light years. And there's accumulating evidence that there may be at least one supermassive black hole at the center of our galaxy, and nearly all galaxies, actually. Now, what's a quasar? The name comes from quasi-stellar, that is, like a star, quasi. Not a star, but like a star. And it's a radio source. So quasi-stellar radio source is a quasar. These are the most distant objects in the universe. And they're believed to be the centers of distant galaxies. So they're so far away that they probably formed soon after the beginning of the universe. One quasar is believed to be 13 billion light years away. Yeah, 13 billion light years away. Compare that to the age of the universe. It's believed to be 13.8 billion light years. huge amounts of electromagnetic radiation, massive amounts, not just radio sources either, all up and down the electromagnetic spectrum. And it's believed that they're probably due to supermassive black holes at the center of the galaxy. Here's one quasar, a real quasar. And the reason it's so grainy is because it's so far away. And the largest telescopes have difficulty resolving it. This one's thought to have 1 billion solar masses in its black hole. So I mentioned this before, and this is why we, looking out into space, is looking back in time, because light takes a finite amount of time to get to us. Okay, so an object that's 1,000 light years away, we're seeing the light that left there 1,000 years ago. All right. And like I said, 13.8 billion years old is one estimate for the age of the universe. Now, there's one assumption that is taken in order to draw this conclusion. That is that the physical characteristics of the universe have not changed in all that time. In other words, one of them, the speed of light, has not changed since the object emitted its light. If the speed of light were less, then the universe would be a lot older than we think it is. But if the speed of light were greater, then the universe is younger. Or if there was some sort of shortcut that it could have taken. These are based upon the doctrine of uniformitarianism. Sounds like a religion. To some people, it is a religion. In other words, the key to the past is the present. So if you see it the way it is now, and the physical behaviors now, that's the way it was back then too. Okay, galaxies may be a fundamental unit, but even galaxies are organized into massive structures called clusters and superclusters. Okay? One cluster, our cluster, is called the local group. And it's made up of about 40 galaxies that include the Milky Way, Andromeda, and M33. They're all within about 3 million light years of each other. And they're gravitationally bound to each other, we believe. So, any collection of galaxies that are gravitationally bound to one another, and they usually fall in the range of 3 to 15 million years old, light years apart, is considered a cluster. Now, superclusters, some have been identified, where you have several clusters that seem to be associated with one another. Don't ask me how they know. This may be all theory. Is a supercluster. Right. Here's what our local group might look like. Right. Milky Way is right here in the center. Andromeda galaxy's out here. Let's see, where's M33? M33 is this one, Triangulum Galaxy. It's not marked M33, but I know that's it. And then there are others. Right? Different ones here. Some of them are above what you would consider the plane. Some are below, but they're supposed to be linked gravitationally. All right, where do you find those two major galaxies, M33 and Andromeda? Well, you need to find these constellations. Pegasus is one. Andromeda is the other. Right? Andromeda, let's see. Yes, I think Andromeda is kind of one of the asterisms in Andromeda is shaped like a W. It's not a perfect W, but it has star, 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 kind of like that. The constellation Andromeda is of a woman, Andromeda, from Greek mythology. But this W, certain times of the year, the Big Dipper is down too low, below the horizon. So sometimes it's hard to find the North Star. Of course, the North Star, Polaris, is going to be visible all year round in the Northern Hemisphere. But the pointers are below the horizon. So this is one that I used to use to find the North Star. Because if you sort of use that as a cup, it points to the North Star. So when Big Dipper is below the horizon, Andromeda is above the horizon. And it's pointing toward the North Star. You can't see it in this picture, but it does. It does do that. No, let's go back. Pegasus, here's the Andromeda. Right? And here's the Triangulum. Here's the Triangulum asterism right here. And this is the Triangulum galaxy. There it is. It's pretty. Now, we're really going to start speculating. It wasn't bad enough that we have to infer black holes. We can't actually observe them. We can observe around them. Now we're going to go even further afield to dark matter. It's an unidentified, uncharacterized, non-luminous, it doesn't emit light, type of matter in the universe. It does have mass, and that's the reason that it's speculated, because it's believed that there's not enough mass in the universe to do what we see based upon what we understand about the universe, right? So dark matter, with our current set of laws about the universe, is required. But if our laws change in the future, maybe dark matter will go away. But for now, we need dark matter to make the models work. All right. So these other indications, the speed of revolution, gravitational behavior of stars and galaxies, indicate that there's much more matter there than we see. But we don't know what kind of matter it is, because normal matter, right, emits radiation under certain conditions. So we should be able to see something if it were normal matter. Right? And we're saying that upwards of 90% of the matter of the universe we can't see. I'm not a physicist. I'm not a cosmologist. I'm not a professional astronomer who theorizes these things, but that is a stretch for me. Maybe it's not for them, but 90% of the matter you can't see it. That's a pretty tall order. For example, the Milky Way is believed to be embedded in a sea of dark matter that could extend as far as 150,000 light years away. Maybe, maybe not. It was referred to as missing mass as early as the publication of Isaac Newton's Principia, because they did some quick calculations and said, whoa, wait a minute, right? If this is true, then there are certain observations in space that just don't work. So they proposed missing mass. But nobody did much with it then. In 1933, the term dark matter was introduced for this missing mass as an explanation for the behavior of galaxies. This was done by Fritz Zwicky. And he was investigating a cluster of stars called the Coma Cluster and comparing their observed mass to their expected mass. Now, don't tell me to give you any details because I don't know. But that 1933 was when this term was first introduced to describe missing matter, missing mass. Later investigations looked at gravitational lensing of background objects by galaxy clusters. So you remember bending of light? Well, if you have an object back here and you have a cluster of galaxies here, and the observer is over here, then what happens is this concentration of mass here causes a lensing effect. And the light is bent around like that, and it's bent around like that. So you actually see two or more images of the same galaxy behind this cluster. Now, the fact that this happens was also predicted by Einstein's law of general relativity, theory of general relativity. But in order to account for this concept, there's not enough mass in these galaxies to do it. So that's just another supporting observation for dark matter. Some researchers are looking at temperature distributions of hot gases in galaxies and clusters. And they say it can't be. These temperature distributions are not possible unless you have more matter. I don't know how they assume that or how they develop it, that theory, but that's the work that's been done. Another one that's been a massive project with a space telescope to boot were patterns of anisotropies in cosmic microwave background. Okay, let me back up a little bit. What do we mean by cosmic microwave background? Everywhere you look in the universe, without substantial stars to get in the way, you see microwave radiation, right, coming at you. And it's all almost the same from any direction you look. And the reason we have to look at it in the microwave realm is based upon another theory called the Big Bang. And I'm going to describe that to you in detail in just a minute. But what that means is it's leftover radiation from the beginning. And it can be seen in any direction. But when the skies are scanned from space for this background radiation, you see anomalies, differences here and there. Those are called anisotropies. Okay, that's where that word comes from. The problem is dark matter might explain them, but also the data processing methods that were used could also have produced these odd patterns without the use of dark matter. Right? So there's still a good bit of controversy for that one. And if there's one thing scientists love to do, it's argue. They argue almost as much as lawyers do. Another investigation is gravitational wave studies. Right? And we'll talk about that in just a second. Gravitational waves were also proposed by Einstein's theory of general relativity, and they have been observed. We have observatories, and I'll describe them in just a minute. All right, so the consensus among astronomers, physicists, cosmologists is that dark matter is primarily not yet a characteristic of subatomic particles. Right? It's not populated by protons, electrons, neutrons. And there's a lot of effort going on to detect just what kind of particle is it. It could consist of neutrinos. Right? Neutrinos are very small subatomic particles. No, wait a minute. I said they're not subatomic particles. They're not normal subatomic particles. Neutrinos are subatomic particles. There's some speculation as to that they may be due to black holes. Maybe there are more black holes out there than we realize there are, accounting for all this matter. So there would have to be a lot of them. Brown dwarfs that we haven't identified yet, right? Neutron stars that are not emitting radio beams, and other potentially high mass material that we haven't even identified yet. What are these high mass materials? Well, one possibility is they're called MACHOs, which is short for massive compact halo objects. I don't even know what that means. But there are a lot of theories out there. And there's an explosion of work in that area. And it's all based upon the fact that our current understanding of the universe requires that dark matter exists. If it doesn't, we can't explain the way the universe is functioning. There could be WIMPs, or weakly interacting massive particles. Okay? We don't know. All right, I've used the term cosmologist. I need to find the term. Cosmology, from the word cosmos, which is Greek for good order or good arrangement, is the study of the structure and the evolution of the universe. It's just that simple. Electromagnetic radiation from galaxies are received. Astronomers propose models for the structure of the universe. Okay. That seems fairly obvious from what we've studied so far in this chapter. From work accomplished so far, most of the galaxies occur in clusters, or some even in linear filaments. One of them even is called the Great Wall. One conclusion that we can draw from all this information is that galaxies are not evenly distributed in space. They occur in clumps, here, here, here. And if we subscribe to uniformitarianism, then we have to go backwards in time to explain how they got that way. How far away are the galaxies? Remember, we talked about parallax for nearby stars and measuring the intrinsic, the absolute magnitude of objects versus their apparent magnitude, and we can judge distance that way also. But that only takes you so far. We need other ways to judge distances. So this is absolutely essential for cosmologists to model the universe. They need to know distances and spacing between the stars, galaxies, superclusters, clusters and superclusters. Okay, so we moved on from that earlier distancing techniques, and nearby galaxies can be distanced using the relationship between this absolute luminosity and the pulsing frequency of a special kind of star, the Cepheid variable star. They were first identified in the Cepheid galaxy, I think. Cepheid galaxy, or it might have been a Cepheid star cluster. Don't hold me to that. This special kind of star became a yardstick. In other words, if you could identify a Cepheid variable star, then you knew exactly its absolute magnitude. That had been proven. So once you can identify this Cepheid in a faraway galaxy, find one. If you have to find one first. Then, based upon its variable period, that is a key to its absolute brightness, its absolute magnitude. And then you measure the observed, you observe its relative brightness and ratio those using the law of the inverse square law. And with this Cepheid variable, we can go up to tens of millions of light years away. Okay, the story of how it was discovered was an interesting one. The Harvard College Observatory had so much data coming in, photographic plates. This was back in the early 20th century. So much information in photographic plates, they didn't have enough scientists to analyze them. So they hired women. I think I've seen pictures, and they're only women, to were employed by the observatory to read these plates and measure the relative, the observed brightness of these stars, these objects in their plates, and then catalog them. And they were called computers. All these women were called computers. Henrietta Swan Leavitt was one of them. And she was working on, her area was working on the Small Magellanic Cloud, that faraway galaxy. So she used the HR diagram that we've seen before and the luminosity of closer stars to calibrate that diagram out to about 35,000 light years. All right. That was the first step. Calibrate your measurement, measure your yardstick. Oh, by the way, Miss Leavitt was deaf, which probably enabled her ability to concentrate, my guess. Okay, there's more to the story than that. It's interesting the way she managed to identify these variable stars and calibrate their period of variable, right? They would give you a variable signal, and calibrate that period to their distance. Second method, right? That's out to what, about 35,000, I said? 35,000 light years, okay? Then the second step was to use Doppler shift of light in rotating spiral galaxies, right? So we could determine their intrinsic luminosity based upon these Cepheid variables that were determined in them. So here's the overlap between that first method I mentioned just now and this method, the Doppler shift. So when a galaxy is rotating, part of it is rotating toward you, even if it's like this, facing like this. You just have to pick the right one. And the stars moving toward you would Doppler shift toward the blue, as they're moving toward you. But those moving away would be Doppler shift toward the red. And that Doppler shift, once calibrated with the Cepheid variables, could be used to determine their intrinsic luminosity. This method could go out to 600 million light years. So there's quite an overlap there, and the ability to go greater distances. Also, this Doppler method then was also corroborated with the established intrinsic luminosity of type 1 supernovae. Right? That's another way. So the type 1 supernovae, remember the white dwarf that accumulated mass to exceed the 1.4 solar units. And that tended to be a very regular, predictable luminosity. So they knew the intrinsic luminosity of these type 1 supernovae, and they could corroborate and calibrate with this other test. And then they could go out even further, 650 million light years. Now, all these previous methods rely on the inverse square law, comparing the absolute magnitude and the observed magnitude. And this comes out of your textbook, I believe. That could be used to determine their distance. If you know both the intrinsic and the observed, the absolute and the observed, then you could correlate them to their distance. Finally, we needed a new method to connect with the limits of these Cepheid, Doppler, and type 1 supernovae methods. What would connect with those and then take us further? We needed Edwin Hubble. Remember, he classified the galaxies, but that wasn't all he did. He also examined the spectrum of these different galaxies and noticed that their spectral lines were shifted. You would expect to see a spectral line for a particular element, but it would be shifted toward the red, which means that there was a Doppler shift, right? The galaxy, and this is the case here, is the whole galaxy was moving away. It was receding from you at very high speed. He did, to be fair, he did notice that some of them were shifted toward the blue spectrum. So those galaxies were moving toward us, but there were only very few of those. Most of them were red shifted. All right, So that's what those two things mean. Blue shift, red shift. And the analogy is with sound, right? If a train is moving towards you, then as it passes, you notice that the pitch decreases. In other words, it goes from a high note to a low note. And in order for this to happen with light, the motion of the object relative to the observer has to be a significant fraction of the speed of light. Okay. Now I'm going to explain in a few minutes, but this statement is true. The Doppler shift that is observed, this red shift, is not so much due to the object's movement through space as it is to the expansion of space-time itself. It's like the galaxy is just along for the ride. And space, the universe itself, is expanding and taking the galaxies with them. What Hubble noticed was that the farther away the galaxies were, the more they were redshifted. So now it could correlate distance with redshift. And this overlapped with the previous technologies, right, for determining distance. So they have to overlap, otherwise you can't figure one where one leaves off and the other one begins. Okay. So as a result of this work, since the farthest away galaxies were extremely redshifted, he concluded that the universe was expanding. That's the short version. And here's a chart. Distance in megaparsecs, 10 to the 6 parsecs. Virgo is relatively close to us. And its recessional velocity is calculated from its redshift is relatively low. But this one, Hydra Galaxy, is way, way out there. Actually, these are galaxy clusters. Excuse me. This is the Virgo cluster, Boötes cluster, Hydra cluster. And by the time it gets to this velocity, it's 20% of the speed of light. Kilometers per second. Okay. And Hubble calculated what's come to be known as the Hubble constant, which is basically the slope of that line. So 71 kilometers per second for every megaparsec. Right? So if you know how to take a straight line and determine slope, rise over run. So if you take the rise here, like from here to here, and then the run from there to there, divided, you get 71. That's the slope of the line. So all you have to do now is determine the redshift and its corresponding relationship to the velocity. Right? And that's a calculation based upon the speed of light and its relationship to stretching the wavelength. Right? And you can do that with this equation. Speed of light equals wavelength times frequency. So if this wavelength is not where you expect it to be, then you can use that relationship to say, all right, what fraction of the speed of light is it actually? So you would take the frequency and it would be a constant. You would take the observed wavelength and then you would calculate what is the speed that would have to give you that. And then ratio it. Well, actually, that would tell you the recessional velocity. How fast is it receding from it? Okay, so what can we do with this Hubble's law? The greater the recessional velocity of the galaxy, the farther away the galaxy. So the age of the universe, don't ask me how they got this formula, but the age of the universe in billions of years is equal to this value divided by Hubble constant. So 71 into this gives you the age in billions of years. Okay, so that means if we calculate the Hubble constant in several different ways, then each one of them is going to give you a different value, which means a different age to the universe. So that's why it's important to accurately determine the Hubble constant. At present, it's in the neighborhood of 71 kilometers per second per megaparsec. So what does it mean if Hubble's right and all the galaxies are receding from us? Right? Does that mean we're at the center of the universe? No. If in fact we do live in an ever-expanding universe, every galaxy is receding from every other galaxy. So it doesn't matter where you are in the galaxy, they all seem to be moving away from you. So here's an analogy. Say you got, you're making raisin bread. Right? You got the dough here that's started to rise. And you got, here's a raisin. And this raisin is 2 centimeters away. And this raisin is 15 centimeters away. And this raisin is 20 centimeters away. You let the dough rise. It keeps rising. Now, these two raisins are 4 centimeters apart instead of 2. Or these are 30 centimeters apart. These are 40 centimeters apart. Right? They're all moving away from each other. Why? Not because they're moving at speed through space, because space itself is expanding and taking them with it. See? Think of that loaf of bread as all the space in the universe. And here, there's just more space. So another thing to take from this analogy is that the greater the initial distance from the raisin, the faster and farther the other raisins are moving. Right? So these two are closer together. So their relative change is 2 centimeters versus 2 where it used to be. Let's see. Yeah, the distance was 2 centimeters. Now it's 4, so it's like 2 to 2, 100%. Let's see. Is that the way to look at this? So if this one's 15, now it's 30. So it's still the same ratio, right? 15 to 15 is 1 to 1. 20 to 20 is 1 to 1. But how did they get there? How did this one go from 15 to 30? Well, it had to go a lot faster than this one did from 2 to 4. So I mentioned calculating the age of the universe earlier. And if the Hubble constant is in fact 71, and we use that equation, then we get 13.8 billion years. But what if the Hubble constant is not 71? What if it's 50 kilometers per second per megaparsec? Then we find that the universe is actually 19.6 billion years. Right? Going from 71 as you get smaller, a smaller Hubble constant means a bigger universe. So that tells us that we better be good at measuring the Hubble constant. Earlier theories predicted that gravity would eventually rein in the expansion. It would eventually win. And that the universe would expand, 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 expand. But there's so much matter that it would slow down, slow down, slow down. Which means what? The Hubble constant would change. And then it would stop. And then collapse. More recent evidence points toward a flat universe. That's one where the rate of expansion is constant forever. And that's not to say that the universe, the boundaries of the universe expanding into something. We don't know what that is. It's not something, it's not anything. The universe is all we know. So if the universe is expanding, it's just making more space as it goes. Some evidence, though, indicates that the universe might be speeding up, expanding faster and faster and faster. And in order to accomplish that, you need another dark energy this time. Right? If there's energy that hasn't been measured, and we learn from the way stars behave, right, the outward pressure of energy production versus gravity, then extra energy in the form of dark energy that we can't see might be causing acceleration of the universe expansion. All right, so if this position is correct, if we are expanding, then the energy, the dark energy, would have to equal 68% of the universe's mass energy balance. Right? So there we have to take mass and energy all together and say that dark energy accounts for 68% of it. Ordinary matter is 5%, and dark matter is 27%. So now dark matter is not 90% anymore. When we take energy into the mix and have to incorporate dark energy, now dark matter becomes 27% of the total. Dark energy is 68%. It still leaves ordinary matter in a difficult position. Okay, all of this expansion is believed to have come from one point source. At some time in the history of the universe, there was an origin. And they call it the Big Bang. And this is the standard model description. If we extrapolate would be out, interpolate backwards. All those galaxies moving backwards. At some point, 13.8 billion years ago, they must have all been a single point source. And at some instant of time, that point started expanding. A small, hot, extremely dense something that then exploded. Actually, the Big Bang was a derogatory term. It was first proposed in 1927 by George Lemaitre. And it was based on the earlier work of a mathematician. So it was purely theoretical. 1922 work. George Lemaitre proposed it, but he didn't call it the Big Bang. I don't remember what he called it. The Big Bang name was applied to this theory by another scientist who was opposed to it. He had an alternate proposal, Fred Hoyle. And he meant the Big Bang to be an insult to Lemaitre's theory. Fred Hoyle's theory was the steady state model. And of course, with all the evidence we've presented so far, there's no surprise that Fred Hoyle's steady state model is now occupying a well-deserved place in the dustbin of history. Using what we know about classical physics, relativistic physics, and quantum mechanics, all taken into account, we can only, I should have said interpolate, we can only interpolate back to about 10 to the minus 34 seconds after the Big Bang, which seems like really close. But from time 0 to 10 to the minus 34 seconds, a lot happened. Anytime before 10 to the minus 34th, the theories of relativity and quantum mechanics just fall apart. They break down, they cannot predict. So we're stuck at that point. It's believed that initially the universe, when it first started, was populated by photons, packets of light, pure energy. By the time we reached 4 seconds after the Big Bang, we had protons, neutrons, and electrons, independent particles. By the time we had 3 minutes from the beginning, from the Big Bang, we had deuterium, which is a form of hydrogen. We had helium, and these are nuclei. They're not neutral atoms, they're just the nuclei, deuterium and helium nuclei in the first 3 minutes. After about 30 minutes old, these nuclear reactions stopped for a time being. And at that point, the theory predicts that we had 25% helium, 75% hydrogen nuclei, a ratio that persists today in interstellar matter. So that's one avenue of support for the Big Bang, because it predicted this amount of each of hydrogen and helium. It also predicts that possibly a little bit of lithium might have been there. Right? If you follow the periodic chart, hydrogen's got 1 proton, helium's got 2 protons, lithium's got 3. So the very simplest atoms were formed in the beginning. And then things stopped for a while. After about 500,000 years, 500,000 years or so, neutral atoms were formed. Things had to cool down a lot so that neutral atoms could form. And then gravity started to kick in. And we started forming stars, and then the stars clumped together in galaxies. So a lot happened between 3 minutes and 500,000 years. So let's review. The Big Bang is supported in 3 major areas. The red shift says that everything's moving apart. The universe is expanding. This cosmic microwave background radiation fills all of space. And the microwave energy itself is interpreted through black body theory as being about 2.7 K. So it's really cold. And over the course of 13.8 billion years, right, it's expanded that much, and the radiation has redshifted and cooled to that point. Now, this cosmic microwave background radiation was discovered by accident. These 2 Bell Laboratory scientists, remember Bell Laboratory with the radio telescope? Well, these guys came along after that, and they built a radio telescope that looked like a big horn of plenty. You've seen those pictures where a big horn filled with fruit and nuts and stuff. Looked like a horn of plenty. And their what it did was it reflected energy. Let me just draw it. Right? So it looked like this. And their detector was down here. So the radiation would come in here, and this curve thing would focus the energy to that point. And that's where they would detect the radio waves. The problem is, for Arno Penzias and Robert Wilson, was that when they were calibrating their instrument, they had this constant noise in the background. It was low frequency. Low frequency microwave noise from here. And they spent weeks and months cleaning it, getting all the bird droppings out of there and what have you. And eventually they looked at every other possible source on Earth or in the solar system. And they had to conclude that since it was the same everywhere they pointed their dish, that it must be coming from space, from the dark of space. It was leftover radiation from the Big Bang. So they stumbled on this concept, but they interpreted it correctly. And they published their work and eventually received the Nobel Prize for Physics in 1978 for this discovery. If you need more information, just go to this link right here, and you'll get probably more than you want. But it's an interesting story. And the other evidence is one I've mentioned before. The ratio of hydrogen to helium is 3 to 1. 75% hydrogen, 25% helium. That's a 3 to 1 ratio. In stars, interstellar material, all of this was predicted by the Big Bang. And then there's this cosmic background radiation. The mapping the cosmic background radiation in the early part of the 21st century indicates the presence of gravity waves that were predicted by Einstein. Right? The mapping of the background radiation says it will cause these anisotropies. right? These irregularities because of the gravity waves that are propagating through it. Now we can measure gravity waves. We're not quite there yet to measure the gravity waves that would be responsible for this cosmic microwave background radiation and its variations. We're not ready for that yet, but we're working on it. And we've got devices scattered around the world. The most advanced devices for measuring gravity waves are located. One is in Louisiana, one is in Washington State, and these together are called the Advanced Laser Interferometer Gravitational Wave Observatories. And they're connected the way they work. There's also one in Italy and one in Germany. They're all being recalibrated with upgrades to their systems. But so far, they haven't been able to detect the low level of gravity wave that's predicted by the Big Bang. Okay. But they have picked up gravity waves from other massive events, like the collisions of two black holes. They have observed that. So we know they're out there. It's just a matter of time before our technology advances and our techniques advance to the point where we can detect these low-level gravity waves that are predicted by the Big Bang. Let's see. Okay, so this is just a slide on the two locations. This one's in Washington. This one's in Louisiana. Notice that they've got long tracks this way, long tracks that way. Well, there's another one going off at right angles that way, and another one that way. They use interferometry, and they need very long distances. They use laser lights that are collimated in such a way that if a gravity wave passes these two arms, they will affect each arm differently because the arms are separated from one another. And they will measure it by laser interference. So it's kind of a complex way to do things, but it has worked. We can say that our current knowledge of the formation of the universe is incomplete. That's an understatement. There's a lot more work to be done. And in research community, that's known as job security. Usually, when an experiment is performed, in the analysis of the experiment and how it addresses your hypothesis, you come up with 3, 4, 10, 20, 30 more questions based on what you learned. So there's no ceiling to the research opportunities. Now, and the standard model as we've described it so far of the Big Bang has some gaps in it, some theoretical holes. And in 1980, the standard model was modified by Alan Guth of Massachusetts Institute of Technology. And he introduced this concept called the inflationary model. He proposes that rather than uniform expansion, he said during the beginning of the universe, between about 10 and 35 seconds after it started, there was a rapid inflationary period. And large numbers of separate regions were formed as they separated and expanded away from each other. Okay, that's the first precept, this inflationary model. That happened really fast and lots of separation occurred between them. Okay, here's the problem. We only occupy space in one of those regions, which means they moved away at speeds exceeding the speed of light, which means now no information from those regions will ever reach us. Right? The theory is that they're out there and they're expanding too, but we'll never know it because this inflationary period, the inflation was faster than 3 × 10⁸ meters per second. So we can only detect information from part of the universe, what we call the observable universe. Now, you can speculate, and this may have been where it came from, speculate about multiple universes, right, going on parallel to one another, and none of them know about each other. This is labeled the multiverse. I don't think that's what Guth meant by the inflationary model. He wasn't talking about multiverse, but some people might, you know, just take a short jump to the left and propose the multiverse. In fact, they've already done that for a movie. Hollywood made a movie called The One. It's entertaining, but highly unlikely to actually exist. Okay. You know, I may have misspoken there. Let's see. These regions did form at between 10 and, no, that's wrong. 10 to the minus 35 seconds. That should be my mistake. Let's see. Where? Here it is. That should be 10 to the minus 35th seconds. I'll make all these corrections and repost the documents in Blackboard. 10 to the minus 35 seconds is when the expansion, approximately when the expansion took place. Between 10 to the minus 35th and 10 to the minus 30 seconds, you have this rapid inflationary period. This is what it looks like on a graph. So here's the time scale, right? And here's the radius of the observable universe. And because this expansion happened faster than the speed of light, now there are parts of the universe that we cannot observe. So we're just left in our own pocket observing what we see here. And during this period, we had an approximate 10 to the 50th increase in the volume of the universe. Right? So between 10 to the minus 6 centimeters up to 1 centimeter. So that might not seem like much, but it's 50 orders of magnitude increase. And then the inflationary period stopped and went back on a steady state. This is an artist's conception, right? We have this inflationary period, right? You have a little bit of time at the beginning and the inflationary period here, and then it started a steady increase in size from about 380,000 years. This is the time where we're supposedly observing the afterglow. That cosmic background microwave radiation comes from this period. And then during this period, the Dark Ages is when there was no light being emitted because we didn't have stars yet. Right? So that's the Dark Ages. And then here we start to see the first stars, and it's believed that the first stars were massive and they burned out very quickly. And nearly all of them exploded in supernovae and scattered heavier elements into the space from which secondary and third generation stars would form, and their planetary systems could form with the heavier elements in them. So it's fairly obvious that our solar system and our galaxy did not form from primordial material. There had to be a time when the heavier elements were produced first before they could be accreted into our solar system and others like it. Okay. And now they think during this period that dark energy is taking over and exceeding the force of gravity and causing the universe to expand even further. All right. If the inflationary model is correct, the entire universe, including everything we can't see, is huge. It's gigantic. And the portion that we observe is only a tiny fraction of the whole. So just when you think things can't get any bigger, if this model is correct, oh yeah, the real universe is much, much bigger than we ever thought possible. All right. So that's the best theory we have so far, and that's the one that everyone agrees upon. Most of the scientists accept it and are working around it, but even though they accept it, they always leave room in their minds for either modifications to it or even replacements for it. Right, so just because most scientists accept that now doesn't mean that they treat it as gospel. All right, that's it. Chapter 18 and for the semester.